Hello there, and welcome. You've found your way to Science for Sleep, where curiosity drifts gently into rest, and where even the most fascinating questions can end not with answers, but with a quiet mind. If you've come here looking for a place to unwind, to slow down, or to find a little wonder before sleep, you're in the right spot. Tonight we're going to explore a question that hums just beneath everything. It's not loud, but it's always present. It's the reason the stars burn, why your hands are warm, why nothing ever really stays still. It's about energy, what it is, why it matters, and most intriguingly, why nothing in the universe ever truly stops. But before we begin, I'd love to know where you are right now. Not just the place on a map, but what time it is for you. Are you tucked into bed in the early hours of morning, or settling down after a long day just as the sun sets? Maybe you're listening with one headphone in while the world around you is still awake. It's funny, isn't it? A topic like this, about the constant motion of everything, and yet here we are, choosing to sit still and think about it together. If this quiet little corner brings you even a moment of calm, if it helps you soften your thoughts or get a little closer to sleep, it would mean a great deal if you liked the video or subscribed. It helps others find this space too, others who might also be searching for a slower rhythm or a gentle way to end their day. Now don't worry, this won't be a lecture. There won't be any pop quizzes or rapid facts flying at you, just a slow, careful exploration of something that might seem invisible, but shapes everything around us. You don't need to remember anything. In fact, it's perfectly fine if you drift off halfway through. That's kind of the idea. So go ahead, take a deep breath, let your shoulders relax a bit. Whatever your body is holding on to, you can set it down for a while. There's nothing urgent here, just you, this voice, and a quiet curiosity about how the universe works. Let's begin with something small. Picture your phone screen, glowing softly in the dark. The light from that screen is made of energy. Not metaphorical energy, but literal packets of energy called photons. Those tiny bits of light were created when electricity flowed through tiny wires, powered by a battery that was charged using electricity pulled from your wall, which came from a generator powered by heat or wind or water or the sun. All of that movement, all of those changes were just energy moving from one place to another. It sounds like a lot, but this kind of thing is happening all the time. In fact, it's happening in every moment, everywhere. From the glow of a street lamp to the sound of your breath, from the turn of the earth to the heat coming off a cup of tea, everything we experience is part of a long, continuous movement of energy. So what exactly is it? The word gets used in so many different ways that it can feel a little fuzzy. We talk about people having good energy, or feeling drained, or bouncing with energy after a nap. In physics, though, it has a very specific meaning. Energy is the capacity to do work. That sounds a little mechanical, but all it really means is that energy is what allows things to happen. It's what lets things move, change, heat up, light up, grow, or fade. Whenever something happens, and I mean anything, from the tiniest vibration to the birth of a star, energy is involved. Sometimes energy takes the form of motion, a car rolling down the street, a falling leaf, a comet streaking through the sky. This is kinetic energy, energy of movement. Other times, energy is stored, like in a wound-up spring or a book balanced on the edge of a table. That's potential energy, waiting to become something else. The moment the book falls, potential becomes kinetic. Nothing was added or lost, just changed form. And this is one of the most important things about energy. It doesn't disappear. There's a rule in physics called the first law of thermodynamics that says energy can't be created or destroyed, it only changes form. This might sound simple, but it's actually one of the most profound ideas we have about the universe. No matter what you do, no matter how small or how large, the energy involved in the action isn't gone when it's over. It's just moved somewhere else, become something else. That idea alone reshapes how we look at everything. It means the warmth from a hug, the power in a lightning bolt, the buzz of a refrigerator, the chirp of a bird. All of it is part of a shared, ongoing process. Nothing added, nothing taken away, just movement. Now let's shift the focus a bit. You might be lying still right now, barely moving, listening quietly. But even if every muscle in your body were perfectly still, you wouldn't be. Your heart is using chemical energy to keep beating. Your brain is firing tiny electrical signals, converting the sugar in your blood into thought. Your cells are busy processing oxygen, repairing themselves and keeping you alive. All of this takes energy. In fact, the only reason we can survive is because of this constant transfer. Food isn't just something we eat for comfort. It's stored chemical energy, originally captured by plants from sunlight. When you eat, you're taking in that energy, breaking it down and repurposing it to fuel your body. Every step you take, every word you think, every blink of your eyes, all of it is powered by something that was, not that long ago, part of a sunbeam. That might sound poetic, but it's also quite literal. Plants use photosynthesis to turn sunlight into sugar. Animals eat the plants. We eat both. And then our bodies use that energy to move, to think, to grow. The sunlight doesn't vanish. It just goes through a few costume changes. The idea that energy never stops can feel a little hard to grasp at first. After all, things clearly do stop, don't they? A spinning top slows down and falls over. A candle burns out. A song ends. A fire goes cold. But what's really happening in those moments isn't that energy is vanishing. It's being transferred or transformed. Take the spinning top. It's moving because of kinetic energy, but over time that energy gets transferred to the surface it's spinning on through friction. It also becomes heat in the air around it. Eventually that energy is spread out in a way that we can't easily notice, but it hasn't been lost, it's just moved on. A candle, when it burns, is combining wax with oxygen, producing heat, light, and carbon dioxide. The flame might go out, but the heat remains for a while. The light has already travelled far beyond your room. The carbon dioxide floats into the air, maybe into a nearby plant, which might one day become another candle. The process continues. That's the thing about energy. It doesn't vanish, it just becomes harder to track. Like a drop of ink in a vast ocean, it spreads out, becomes part of something larger, less visible, but it's still there. Now imagine for a moment what would happen if something actually did stop, completely, not just resting on a table or taking a nap or going into standby mode. I mean absolutely, perfectly motionless. No vibration, no flicker of heat, no electrical pulse, no movement of particles. That would be true stillness. In physics, we have a name for the coldest possible state something can be in. Absolute zero. It's a theoretical point where there's no thermal motion at all. And yet, even there, quantum mechanics tells us that particles still have a kind of jitter, a tiny, unavoidable hum, 0-point energy. It's as if the universe simply refuses to let anything be completely still. This is one of the strangest and most beautiful things we've learned. That stillness, as we understand it, is a kind of illusion. Even in deep space, where temperatures hover near absolute zero and no light shines, particles still wiggle. At the smallest scales, everything buzzes, shifts, pulses. The idea that nothing ever stops isn't just a nice metaphor. It's a literal truth about the nature of matter. Your body right now is full of those tiny movements. You might not feel them. That's okay. You don't have to. But they're there. Atoms vibrating, molecules bouncing, fluids flowing, signals firing. You're never really still, not even in your deepest sleep. So what does that mean for how we live? Maybe not much. Practically speaking, you'll still need rest. You'll still need breaks. But understanding that nothing ever stops, not truly, is a reminder of how connected we are to everything around us. Every movement you make continues as ripples somewhere else. Every bit of warmth you feel is energy that came from somewhere and will go somewhere else. You're part of a continuous stream, not a separate drop. And maybe that's comforting. In a world that sometimes feels chaotic or unpredictable, The quiet persistence of energy can feel like an anchor, a kind of rhythm beneath everything, not loud, not urgent, just steady. If you've made it this far, you're probably starting to feel that rhythm now, the slower pace, the way ideas gently fold into one another. That's how energy moves too sometimes, not in explosions or flashes, but in soft transitions, in the way heat fades from tea, in the way your breathing slows when you're almost asleep. So now that we've settled into the idea that energy doesn't just vanish, let's talk more specifically about what it is. Not metaphorically, not as a feeling or vibe, but in the clearest, most grounded way possible. When scientists talk about energy, what do they really mean? It starts with the idea of work. Not work like going to your job or writing emails, although those things do involve energy too, but work in a physical sense. Moving something against a force. That sounds a little abstract, so let's break it down further. If you lift a box from the floor and place it on a table, you're doing work. You're moving that box upward against gravity, and to do that, you need energy. Where does that energy come from? From your muscles. How do they get it? From the food you ate earlier. That food had stored energy, and your body turned it into motion. It's a transaction. Energy in, work out. But energy doesn't always look like lifting things. It can be less obvious. Heat is energy. Light is energy. Sound, electrical currents, the chemical reactions in your body, the pressure of wind against a window, all of it involves energy in some form. The key is change. If something changes, moves, heats up, cools down, lights up, breaks, bonds, then energy is involved. What's interesting is that there isn't just one kind of energy. There are several forms, and they all play different roles in how things happen. Kinetic energy, like we talked about before, is energy in motion. A running dog, a flying bird, even the vibrations in a guitar string, they all hold kinetic energy. Then there's potential energy, which is stored. Think of a roller coaster at the top of a hill. It's not moving yet, but it has the potential to. The moment it starts to descend, that potential turns into kinetic energy. It didn't appear out of nowhere. It was there all along, just waiting to be released. Thermal energy is another form. That's the internal energy of an object due to the movement of its atoms and molecules. It's what we feel as temperature. When you boil water, you're increasing its thermal energy. The molecules move faster, bump into each other more, and eventually turn into steam. Even something as everyday as a warm blanket on a cold night is about thermal energy, either holding on to it or transferring it from you to the surrounding air. Chemical energy is stored in bonds between atoms. It's in food, batteries, gasoline, and even wood. When a match is struck and a flame appears, chemical energy is being released in the form of heat and light. It's not being created. It was always there, locked inside the material, just waiting for the right trigger to let it out. Then there's electrical energy, what moves through wires to power your lights or your laptop. It's the flow of electrons, tiny charged particles. Magnetic energy is related to that, and they often work together like in motors or generators. Nuclear energy, perhaps the most dramatic form, is stored in the nucleus of atoms and released during fission or fusion, as in nuclear reactors or stars. These forms can be transformed into one another. That's the beauty of energy. It's flexible, not just persistent, but adaptable. For example, in a power plant, chemical energy in coal might be converted into heat, then into kinetic energy as steam spins a turbine, and finally into electrical energy that travels to your home. That electricity might then be turned into light, heat, or sound, depending on what appliance you use. None of the energy disappears, it just changes its outfit, so to speak. Even your own body is full of these transitions. You eat food, that's chemical energy. Your body digests it and uses some of it to create motion, like walking, or to keep you warm, which is thermal energy. Some of that energy is used for brain activity, which relies on electrical signals. When you speak, you're turning chemical energy into sound. When you smile, you're converting food into motion. and maybe even emotion in someone else. It's all connected. What might surprise you is just how much energy it takes to keep you going, even when you're resting. Right now, your heart is pumping, your lungs are expanding and contracting, and your brain is firing off signals. Your digestive system, even if you haven't eaten recently, is still busy maintaining balance. Your cells are constantly producing proteins, breaking things down, building things up. That's energy at work, and it doesn't stop, not even when you're asleep. There's even a term for the minimum amount of energy your body needs to stay alive while at rest. It's called the basal metabolic rate. It's what you'd burn if you just lay in bed all day doing absolutely nothing. Just existing, breathing, thinking, staying warm requires energy. And that's because nothing inside you ever fully stops. Your body is a living, moving system even in its quietest state. Now zoom out. Look beyond your body, beyond your home, beyond your city. Look at the planet. It spins, orbits, breathes in its own way. The tides rise and fall, winds shift, trees grow, oceans swirl, mountains erode. All of this involves energy moving from one form to another. Solar energy hits the earth and becomes heat. Plants capture that energy and store it. Animals eat the plants. Weather patterns are driven by uneven heating of the earth. It's all part of one massive exchange system. Even the things we tend to think of as solid and unchanging, like rocks or glaciers, are in motion if you wait long enough. Rocks are being worn down by rain and wind. Glaciers flow slowly but steadily. Continents drift. The planet isn't static. It's just operating on timescales we don't normally feel. Now go even farther. Look at the solar system. The planets orbit the sun, pulled by gravity, moving in precise paths that require constant motion. If they stopped moving, they'd fall straight into the sun, but they don't. They keep going. That motion, that orbital energy, is conserved. It's been there for billions of years and will likely remain for billions more. Beyond that, stars burn with nuclear energy, turning hydrogen into helium, releasing heat and light. Galaxies spin. Black holes feed. Radiation travels across the void. Even the background of the universe, the leftover heat from the Big Bang, is still present, still faintly glowing, still moving. It's energy that has been stretching and shifting for almost 14 billion years, and we're part of all of that. Made from the same atoms, powered by the same rules, connected by the same exchanges. One of the most interesting things about energy is that, while we understand its behavior pretty well, we still don't completely understand what it is. We can define it, we can measure it, we can track it, convert it, store it. But ask a physicist for a one-sentence answer to, what is energy really? And you might get a pause. Not because they don't know, but because the question is more complicated than it seems. Some might say, energy is an abstract quantity, a way of describing how much ability a system has to cause change. Others might say, energy is just a number that helps equations balance. But for most of us, the definition is less important than the reality. We feel energy, we rely on it, we live in it. When you boil it down, energy is simply the measure of how things happen, and things are always happening. Nothing rests completely, nothing is ever truly isolated. Even silence has vibrations, even darkness contains photons, even still air is full of motion at the microscopic level. So the idea that nothing ever stops isn't just philosophical, it's a reflection of how the universe works, and whether you're actively thinking about it or not, you're part of that endless motion, a participant in the quiet momentum of everything. It's not something to solve, it's not a puzzle to complete, it's just something to notice, gently, to feel, to rest within. When we talk about energy changing form and never disappearing, there's a law that holds it all together. It's one of the most reliable things we know in physics. No matter where you are in the universe, no matter how much time has passed, this rule still applies. Scientists call it the first law of thermodynamics, and at its core it simply says that energy is conserved. It can move, it can shift, It can look completely different from one moment to the next, but it doesn't get lost. You can't make energy from nothing, and you can't make it vanish into nothing. You can only pass it along, store it differently, or transform it. Think about charging your phone. You plug it into the wall and it fills up with energy. But where did that come from? The wall socket drew it from a power grid. The power grid got it from some generating source, maybe a wind turbine, a hydroelectric dam, or a power plant burning fuel. If you follow the trail back far enough, every bit of energy your phone uses came from somewhere, and it's going somewhere else the moment you use it. It's not like flipping a switch makes energy magically appear. All that's really happening is a transfer. In a way, that's what the first law is constantly reminding us. It's like the accounting system of the universe. Everything adds up. You can't cheat it. You can't hide energy somewhere off the books. It will always show up in the balance, even if it's in a different form than it started. This plays out in ways you don't even notice. When you walk across a room, your body's converting stored chemical energy from food into motion. When you stop walking, the energy doesn't just dissolve. Your body radiates some of it as heat. Some is stored again in different chemical forms. A bit of it is lost to friction, both inside your joints and between your feet and the floor. Not lost in the sense of disappearing, but lost in the sense of being spread out, no longer concentrated enough to be reused easily. But it's still there, part of the total energy pool. That's why energy use isn't just about how much you have, but how concentrated or usable it is. You might have a lot of thermal energy in a lukewarm room, but it's not enough to do much. If you had that same amount of energy concentrated in a small hot fire, you could cook with it, or power an engine. The total amount might be the same, but the usefulness depends on how it's arranged. This is also why machines aren't perfectly efficient. Whenever you use a car engine, a toaster, or even your muscles, some of the energy is transformed into forms you don't want, like waste heat. That doesn't mean it's gone, just that it's no longer in a form that can easily be used again. The engine gives you motion, but it also warms up the air around it. The toaster browns your bread, but also releases heat into the room. Even your body runs warm when you're active, and that warmth is part of the energy flow. Not extra, not free, just another place the energy goes. You see the first law at work every time you notice heat, light, sound, or movement. They're all visible results of energy being converted. In a sense, every lamp that glows or motor that turns is just the universe reshuffling energy from one place to another, according to rules it never breaks. Even burning something, which might look like destruction, is actually a process of transformation. When wood burns, the chemical bonds between atoms break, and new bonds form. That reshuffling releases energy in the form of heat and light. The matter isn't destroyed either. It becomes ash, smoke, and gases. The energy goes outward, the mass changes form, but nothing disappears. There's no vanishing, no magic, just exchange. In nuclear reactions, like the kind that power the sun or certain types of reactors, we see the same law at play. Atoms are split or fused together, and a tremendous amount of energy is released. But even here, the total mass and energy involved remain consistent. They might switch forms, from tightly bound particles to high-speed radiation, but nothing is created from nothing, and nothing returns to it. Einstein's famous equation, E(mc)2, tells us that mass itself is a form of energy. The two are interchangeable under the right conditions, so when energy is released in a nuclear event, some of the mass is simply being converted. The numbers still check out. The universe doesn't skip a beat. There's a kind of comfort in that consistency. When everything else in life can feel uncertain or unpredictable, it's oddly reassuring to know that energy keeps following the same pattern. Even in events that seem chaotic or destructive, a volcano erupting, a car crashing, a thunderstorm rolling in, the first law still applies. Energy doesn't break its own rulebook, even when things look like they're falling apart. This also shows up in the smaller systems. If you look at a cell under a microscope, what you're seeing isn't stillness, it's motion. Proteins shifting, molecules binding and unbinding, ions moving through channels. That activity is fueled by chemical energy, usually in the form of a molecule called ATP. Cells don't create ATP out of nowhere. They build it by processing nutrients, sugars, fats, proteins, and extracting the stored energy from their chemical bonds. That energy is used to keep the cell alive. Once the work is done, the ATP breaks down, and the leftover parts are recycled to start again. The whole system is built on careful bookkeeping of energy. Input, conversion, output, always balanced. You'll see the same principle in weather. The sun heats parts of the earth unevenly, creating differences in temperature and pressure. Air moves to balance those differences, and that motion becomes wind. Water evaporates, rises, cools, and falls again as rain. Every step involves energy shifting, from sunlight to heat to kinetic movement to changes in state. The storm isn't spontaneous. It's a long chain of linked events, each part following the same rule, energy moving but never vanishing. Even the act of thinking, the process you're using right now as you listen, runs on energy. Your brain, which makes up only a small part of your total body weight, uses around 20% of your body's energy at rest. Neurons fire, chemical messengers cross synapses, and electrical impulses move through networks. All of that activity is powered by the same chemical transformations as the rest of your body. Listening, remembering, imagining, they all have a cost, paid in energy. So when you take a step back and look at everything, from the smallest reactions in your body to the movement of planets and stars, you'll notice the same theme. Nothing just happens. Every change, every motion, every tiny ripple in matter or light is made possible because of energy being exchanged, not created, not destroyed, just moved, shifted, spent, stored. It might seem like this law is abstract or academic, but it shapes your daily experience in constant, invisible ways. It determines how long your phone battery lasts. It explains why your coffee gets cold if you leave it out. It sets the rules for how your car engine works, why your muscles tire, why food gives you strength, and why fire feels warm. You don't have to think about it, but it's there, quietly guiding everything that happens. You could look at a sunset and just see colours, or you could see an atmosphere scattering light from the sun, energy that took 8 minutes to travel across space, passing through clouds, bouncing off particles, entering your eyes, activating cells in your retina, sending signals to your brain. Each step powered by energy, each link in the chain accounted for. Or take a more ordinary example. You flip a light switch. Electricity flows through a wire. That energy might have started at a dam, where falling water turned a turbine. The water gained its height from rain. The rain came from evaporated water. The evaporation came from sunlight. That sunlight came from the sun's core where hydrogen fused into helium. All of that is linked. All of that obeys the first law. Nothing added. Nothing wasted. Just passed along. Even when things seem quiet or uneventful, there are transitions taking place. Cooling, shifting, adjusting. A glass of water left on a table is gradually reaching the temperature of the room. That process isn't instant, but it's happening. Molecules are moving, exchanging energy. If you measured closely enough, you'd see the numbers change. You'd watch the balance in action. So much of the world operates this way, by systems in motion, converting energy, moving through stages. You might not notice it happening, you might not feel it, but it's always there. The light above your head, the warmth on your skin, the pressure in your footsteps, all are part of the same constant motion. Not random, not wasteful, just endlessly consistent in how energy continues to move, transform, and stay present. When something ends, like the sound of a bell or the heat from a match, we sometimes assume it's over, but it isn't. The sound spreads into the air, the heat dissipates into nearby objects, the energy becomes part of a broader background. The first law is still being honoured. Always. That quiet consistency, that refusal to break its own rules, is one of the reasons the universe is understandable. It's not chaos behind the scenes, it's structure. It's rules that apply just as well to a leaf falling as to a satellite orbiting. Whether you're looking through a microscope or a telescope, you're watching energy in motion, bound by a rule that never takes a break. And even if we stop paying attention to it, the system keeps running. Because it always has. It always will. Energy doesn't just move in a single way. While it always abides by the same laws, it wears different faces depending on the situation. Two of the most familiar forms it takes are kinetic and potential. These are terms you've probably heard before, maybe in school or maybe just mentioned in passing. But they're not just vocabulary words from a physics textbook. They're constantly in play, everywhere around you, often trading places without warning, always sticking to the rules, never missing a step. Kinetic energy is motion. It's energy doing work right now, not later. When something is in motion, rolling, flying, shaking, spinning, falling, stretching, that's kinetic energy being expressed. The amount of kinetic energy an object has depends on two things: its mass and its speed. The heavier and faster something is, the more kinetic energy it carries. A car coasting down the highway at 60 miles an hour carries much more kinetic energy than a tennis ball flying through the air, simply because of the difference in mass. But both of them, no matter how different in size, are drawing from the same principle. This kind of energy isn't just something you witness. You feel it. The warmth from your hands after clapping, the rush of wind as you stick your arm out of a moving car, the sharp sensation of a sudden jolt. These are signs that kinetic energy is being transferred from movement to heat, from speed to impact. When something moves, it doesn't keep moving forever. Eventually friction, gravity and air resistance slow it down. But remember what we've already seen, that energy doesn't disappear, it's just changing forms. The kinetic energy of a ball rolling on the floor gradually becomes thermal energy in the floorboards and the air. You don't usually notice that shift because the heat is dispersed and subtle, but it's there, quietly keeping the books balanced. Now think about a roller coaster. As it climbs a steep hill, it slows down. The engine or the chain pulling it is doing work, using energy to raise it up. And even though the train isn't moving quickly at the top, it has potential energy. That's energy stored in its position. Because it's high up, gravity has something to work with. The moment it begins to descend, that stored energy turns into motion. Potential becomes kinetic. The train rushes downward, pulled by gravity, converting its height into speed. Potential energy is all about context. It's not active yet, but it's ready. A rock perched on the edge of a cliff, a stretched rubber band, a book balanced on a shelf. All of them hold potential energy. It's stored because of their position or configuration. Nothing might be happening in that moment, but the setup matters. A small nudge, and that energy is released. The most common kind of potential energy you interact with is gravitational. The higher something is lifted against gravity, the more energy it stores. But there are other types too. Elastic potential energy is stored in things like springs or slingshots when they're compressed or stretched. Chemical potential energy is stored in the bonds between atoms and molecules, in batteries, food, fuels. There's even electrical potential energy, where charges are separated and held apart, ready to release energy when allowed to move. These stored forms of energy aren't visible, but their effects are. Light a match, and you see chemical potential turn into heat and flame. Drop a weight, and potential becomes movement. Fire a bow, and the flex of the string becomes the flight of an arrow. In each of these cases, what starts out as a kind of pause, held, poised, quiet, becomes action. That transition is where the beauty lies. Kinetic and potential aren't isolated states. They're constantly trading places. One flows into the other and back again. When you throw a ball into the air, it starts with kinetic energy. It slows down as it climbs, converting that motion into height, into potential. At the peak of its arc, it's motionless for the briefest moment, but full of stored energy. Then it falls, and the energy becomes motion once again. You see this in a swinging pendulum. At the top of each swing it slows down, potential energy is at its maximum. As it drops, the energy turns into motion. At the bottom of the arc it's moving fastest. Kinetic energy is at its peak. Then it rises again, slowing as it climbs, and the cycle continues. The energy flows back and forth, perfectly, unless something like friction or air resistance begins to drain it into less useful forms like heat. Even your body plays with these two types of energy all the time. When you jump, you use chemical energy from your muscles to push off the ground, creating kinetic motion. As you rise, that motion converts into gravitational potential energy. At the top of your jump, just before you fall, your body holds energy in stillness. Then you fall, and it turns back into kinetic energy as you come down. The process is so automatic that you don't think about it, but it's a perfect example of how these energies are constantly interchanging. You don't need a laboratory to see these things in action. Everyday moments are full of this interplay. Take a child on a swing. They start low, are pulled back, gaining potential energy, then released, turning that into motion. They swing forward, up into the air again, pausing for an instant before gravity pulls them back. It's a slow, steady exchange. Push and pause. Energy held, then used. It happens over and over, and it never gets old. Or consider a cup sitting on the edge of a kitchen counter. As long as it's still, it might seem like nothing is going on. But it has potential energy relative to the ground. If someone nudges it accidentally and it falls, that stored energy turns into kinetic energy as it accelerates toward the floor. Upon impact, that energy is quickly transformed, some into sound, some into heat, some into the motion of the fragments if it breaks. What seemed like a simple moment is actually a full cycle of energy transfer. This framework also helps explain why certain activities feel different in your body. Walking on flat ground requires a consistent output of kinetic energy, but climbing stairs involves lifting your weight upward, increasing your gravitational potential energy. That's why it feels more tiring. You're storing energy in your new height, and your body's doing more work against gravity to make it happen. At larger scales, entire systems behave this way. A dam holds back water, storing gravitational potential energy as the water is elevated above the level of the turbines below. When the gates open, water flows downward, converting that potential energy into kinetic energy. That motion then turns turbines, producing electricity. Again, energy is never created, it's simply transformed from one form into another in a sequence we've learned to harness. These conversions don't just happen on Earth. The orbits of planets involve similar exchanges. A comet passing close to the Sun speeds up, converting gravitational potential into kinetic energy. As it moves away, it slows down again. The balance continues across vast distances, under conditions far removed from daily life, but the rules stay the same. Understanding these two forms, kinetic and potential, is like learning a language the universe speaks fluently. Once you start to notice it, you see the push and pause everywhere. In a bouncing basketball, a flying bird, a shifting wave, a rolling storm cloud. All of it is movement and waiting, energy acting and energy preparing to act. There's also a kind of intuition that builds with this understanding. You start to realize that energy doesn't need to be dramatic to be meaningful. Something as small as a coiled spring on your desk contains stored energy. The difference between something ready to fall and something that already has is just a moment, just a release. The shift from pause to push is immediate, but never without cost. Something always gives, something always receives. This balance is how machines work. It's how your muscles lift things. It's how electricity is generated. It's how life moves forward, step by step, shift by shift, in a world where energy always has somewhere else to be. And the more you see it, the more familiar it becomes. The sharp turn of a bicycle wheel, the wind-up of a pitch, the stretch of a rubber band before it snaps back. These aren't isolated events. They're constant rehearsals of the same relationship, stored energy waiting to move, movement becoming storage again, the back and forth rhythm that gives the physical world its shape and texture. None of it happens without context. None of it breaks the rules. It's a constant flow between holding and releasing, between height and motion, between stored possibility and active change. Every moment is shaped by the position of things and their capacity to move. The next time you see something fall, jump, bounce, or sway, you might not say the words out loud, kinetic and potential, but you'll feel the pattern. You'll recognize that what you're watching isn't random. It's just energy doing what it always does. Moving when it can, waiting when it must, but always following through. When we talk about energy and movement, it's easy to picture the obvious examples. A thrown ball, a falling leaf, a running engine. But not everything that's moving looks like it is. In fact, some of the most active systems in the universe appear on the surface to be completely still. Stillness, as we usually describe it, is more of a sensation than a scientific reality. To feel something as calm or unmoving just means that the motion taking place is outside the scale of our senses. It helps to start small. Look at a table, a pillow, a book. To your eyes, it's resting, not shifting, not vibrating, not bouncing around. But if you could zoom in far enough, down to the level of atoms, you'd see something completely different. Those atoms aren't sitting still. They're in constant motion, even at room temperature. The molecules in the air around you are moving too, bouncing off each other and the walls and you. Trillions of tiny collisions every second. You don't see it, but you're immersed in it. What we call temperature is really a measure of how much things are moving at that microscopic level. The higher the temperature, the faster the particles move. That's why heating something makes it expand. The atoms are jostling harder, pushing each other a bit farther apart. Cooling something slows those movements down, but they don't stop completely, not even in deep space. Even at extremely low temperatures, where all the heat has seemingly vanished, atoms still exhibit a slight, unavoidable vibration. This is known as zero-point energy, the lowest energy state allowed by quantum mechanics. At absolute zero, which is theoretically the coldest possible temperature, you'd expect everything to just stop. But it doesn't. Quantum systems can't sit perfectly still. There's always a baseline amount of motion, a kind of built-in fuzziness, a reminder that stillness isn't a complete halt, just a quieter version of movement. This is different from the way we usually think about rest. When we say something is still, we mean it's not moving relative to us, or that it doesn't look active. A parked car, a closed book, a sleeping cat, they're all examples of apparent stillness. But in each of those cases, there's still motion happening at some level. The electrons in the car's metal frame are buzzing with energy. The molecules in the pages of the book are vibrating in place. The cat is breathing, twitching, dreaming, its body busy with internal motion. Even sleep is not an absence of activity. It's a different pattern of it. When you lie down at night and stop moving, it can feel like your body is shutting off, but it's not. Your brain is entering a cycle of rest and repair, cycling through sleep stages. Your muscles are recovering. Your digestive system continues working through whatever you last ate. Your lungs keep expanding and contracting. And even though your body temperature might drop slightly, the motion inside you doesn't stop. Every heartbeat, every nerve impulse, every cell process is still running. Slower maybe, but never at zero. Stillness in the natural world is often a matter of contrast. If you stand perfectly still in a forest, you might think everything around you is quiet and paused. But the wind is moving through the leaves. Insects are shifting in the grass. Tree branches sway just slightly. Light changes from moment to moment. Even if you stop all your muscles from moving, your blood continues to circulate. Your pupils adjust to brightness. Your skin senses pressure and warmth. You're still a dynamic system. just not in a way that's immediately visible. There's a term in physics called dynamic equilibrium. It describes a state where things appear stable, but underneath that appearance, opposing processes are continuously balancing each other out. A good example is your own body temperature. It stays relatively constant, but only because your body is constantly adjusting, sweating, shivering, increasing or decreasing blood flow to maintain that balance. There's no actual pause, just a continuous feedback loop that creates the illusion of calm. Water in a sealed glass at room temperature can look perfectly still, but on the surface, molecules are constantly evaporating into the air and condensing back into the liquid. It's not noticeable to your eye, but the exchange is happening. Molecules are leaving and returning in a steady rhythm, keeping the level of the water steady. Still, but not inactive. This happens in solids too. Atoms in a metal bar aren't fixed in place like statues. They vibrate within their positions in the structure. The colder the bar gets, the less they move, but they never become completely motionless. That's not just theory, it's observable. These vibrations affect how materials conduct heat and electricity. They're measurable. They matter. Stillness, again, is a matter of scale and perspective. Even in things that seem lifeless, rocks, glass, the surface of the moon, there's motion hiding underneath. The atoms that make up a rock are arranged in a lattice, and those atoms vibrate constantly. If you heat the rock, those vibrations increase. If you cool it, they slow down, but they're always there. And over long spans of time, even rocks change shape. Mountains erode, valleys form, soil shifts. The change might take thousands or millions of years, but it's movement all the same. There's a reason scientists describe atoms and molecules using terms like energy levels and excitation states. Nothing sits completely idle. Particles jump between states. Electrons shift positions. Radiation passes through. Light is absorbed and emitted. At every level, even in materials that appear static, there's a steady churn of activity, not random but rule-bound and predictable. You might be sitting still right now. Maybe your hands aren't moving, maybe your breathing has slowed, maybe your thoughts have softened, but you're not frozen in time. The molecules in your skin are in motion. The neurons in your brain are active. Your body is working in 1,000 small ways to keep everything running. There's no visible drama, but there's no true stop either. Some of the most stable things we know, atoms for instance, are only stable because of constant internal movement. The particles inside them don't rest. Protons, neutrons, electrons. They all have energy and position and behavior, shaped by forces that keep them in balance. Remove that energy, and the atom ceases to exist in any meaningful way. It's energy that gives it form, structure, and persistence. This same principle applies to stars, planets, black holes, and beyond. Objects in orbit are in constant motion. A satellite circling Earth might seem to hover when viewed from the right angle, but it's moving at thousands of kilometers per hour to stay in that path. The only reason it doesn't fall is because it's moving fast enough to continually fall around the planet instead of into it. Stability isn't stillness, it's motion with balance. On an even larger scale, galaxies rotate. Cosmic background radiation travels endlessly through space. The universe itself is expanding. The space between clusters of galaxies is getting wider, slowly but steadily. Even in the vast darkness where no stars shine, energy is present, moving in the form of photons, neutrinos, and particles too faint for us to detect easily. Stillness doesn't belong to the cosmos. It's a local illusion, a temporary sense that things have stopped. Our senses are tuned for specific ranges. We can't see the vibration of atoms. We don't hear the movement of blood cells or the shifting of tectonic plates unless something dramatic happens. But the absence of perception isn't the absence of motion. It just means the scale isn't one we're built to observe without tools. Microscopes, telescopes, particle accelerators. These are the extensions we've created to see what our eyes can't, and with them, we've confirmed what the laws of physics have long suggested, that everything is in motion, that stillness in the most technical sense doesn't exist. What you feel when you say something is calm or still is a kind of sensory pause. The noise has lessened. The pace has slowed. You've dropped out of immediate motion, but the systems underneath keep going. You don't need to see them. They'll keep working whether you notice them or not. This is part of why things can seem peaceful without actually being stopped. A pond at dawn, a room just before sleep, a breath held in the chest. These are moments where surface motion disappears, but internal motion continues. And once you become aware of that, not just intellectually but viscerally, the quiet starts to feel different. Not empty, not frozen, just quietly alive. The hidden motion inside everything doesn't stay hidden forever. In many cases, it eventually shows itself, and two of the most familiar ways it does are through heat and light. These aren't abstract ideas. They're forms of energy you experience constantly, without needing any background in physics to recognize what they are. You feel them on your skin, see them in the world around you, and respond to them almost automatically. They are steady, reliable signals that something is happening, that energy is on the move. Heat is one of the clearest signs of motion on the smallest scale. When atoms and molecules vibrate more rapidly, what you feel is warmth. The faster they move, the higher the temperature. That's really all heat is, not a substance or a force, but a way of describing how much internal energy is present in matter. Every warm object, from a stove to your own body, is just a dense collection of moving particles bouncing off one another. Touch a metal spoon that's been sitting in hot tea, and it's warm not because heat travelled through it instantly, but because the rapid vibrations of the tea's molecules passed their energy into the metal, which then passed that energy along its length. Molecules bumped into other molecules, and the motion spread. You didn't see it happen, but your hand registers the change. That's thermal conduction. One of the many quiet transfers energy makes. But heat doesn't just need contact. It also moves through the air, through fluids, even through a vacuum. The warmth you feel from sunlight isn't because the air between you and the sun got hotter. The heat comes through space itself, riding on waves of radiation. That kind of transfer is called thermal radiation. It's how the heat from a fire warms your face even if you're not close enough to feel the air moving. Heat is deeply tied to the idea of entropy, the tendency of energy to spread out, to move from where there's more of it to where there's less. That's why your coffee gets cold if you leave it on the table. The heat doesn't disappear. It just flows into the surrounding air, into the table, into the room. Eventually everything reaches a kind of equilibrium. The motion levels out, but even then particles are still moving, still trading energy. There's no true end point, just balance. This flow toward evenness, toward less concentrated energy, happens all the time. It's why ice melts in a drink, why food cools on a plate, why engines need constant fuel. Concentrated energy, like heat in a stove or chemical energy in gasoline, does useful work while it's moving from high to low, but once it's spread out, it's harder to use. The energy is still there, but it's no longer organised in a way that lets it power something specific. That organisation matters. When energy is concentrated, it can be harnessed. That's why we burn fuels, why we eat food, why we plug devices into outlets. We're looking for pockets of energy that haven't yet spread out, places where motion is ready to happen. Once we use it, the energy goes somewhere, but it's not as useful anymore. That's not a failure. It's how the system works. Light behaves differently, but it's still energy. It doesn't come from motion inside objects, but from electrons jumping between energy levels. In atoms, when an electron absorbs energy, from heat, from a collision, from some external force, it can move to a higher energy state. But it doesn't stay there. Eventually it falls back down, and when it does, it releases the energy it absorbed. That energy often takes the form of a photon, a particle of light. The colour of the light depends on how much energy is released. Blue and violet photons carry more energy than red or orange ones. That's why heating something until it glows usually starts with a dull red and moves toward white and blue as the temperature rises. The atoms are more energized, their electrons jumping and falling more energetically, releasing more energetic photons. That's what you're seeing when a piece of metal glows in a furnace or when the filament of an old-fashioned light bulb lights up. The material is hot enough that electrons inside the atoms are excited to the point of releasing visible light. In the case of the sun, it's the extreme heat from nuclear fusion, the joining of hydrogen atoms, that releases a cascade of energy, some of which becomes the visible light we rely on. But not all light comes from heat. Fluorescent lights and LEDs release photons through different processes, often involving electricity or chemical reactions. Bioluminescent organisms like fireflies or deep-sea creatures create light using enzymes and proteins. The energy transitions are the same in principle. Energy is absorbed, electrons shift, and photons are released. But the source of the excitation isn't thermal. Light is strange in other ways too. It behaves like a wave and like a particle, depending on how you observe it. It doesn't need a medium to travel through. It moves perfectly fine through a vacuum. It carries energy across vast distances without losing speed, and when it reaches you, it can trigger chemical changes in your eyes that become vision. It's not just energy on display, it's energy becoming information. We don't just see light, we respond to it. It regulates our sleep cycles, triggers photosynthesis in plants, fuels solar panels, creates shadows and reflections. It marks the passage of time. The sun rising and setting shapes how we organize our days, even in places where artificial lights are always available. Light connects us to what's happening, both immediately around us and far away. Heat and light together are two of the main ways energy moves through the world. They interact constantly. A campfire produces both. Warmth you can feel and light you can see. A star gives off both, travelling across space in straight lines until it hits something, an eye, a leaf, a wall. That impact can do work, change temperature, start a process. It's all part of the flow. These forms of energy also leave behind subtle traces. Infrared cameras can see heat that's invisible to the human eye. Sensitive instruments can detect the light from stars billions of light years away. Photons emitted long ago are still arriving, carrying with them the story of where they came from. Even after the source is gone, the energy keeps travelling. That's how we're able to observe ancient galaxies or detect the glow of the early universe. Light is a message in motion. It keeps going until something receives it. When you warm your hands by a heater, the heat you feel is not created in that moment. It's been stored, converted, guided. When you see light reflected off a wall, the photons have bounced from surface to surface, sometimes absorbed and re-emitted, sometimes changed in direction or intensity. But they're still moving, still transferring energy. What feels like simplicity is actually the result of countless interactions. We often associate heat and light with intensity, with fire, sunlight, engines and explosions, but they also show up quietly, a candle's flame, a warm patch on a tile floor, the glow of a computer screen in a dark room, the body heat of another person nearby. These small signals are just as real, just as meaningful. The scale is smaller, but the process is the same. Energy moving, being used, travelling outward. Even in darkness there is still light, just not always in the range our eyes can detect. Infrared, ultraviolet, radio, X-rays. These are all forms of electromagnetic radiation, just like visible light. They differ only in wavelength and energy, but they're part of the same spectrum. When you heat something, it emits radiation across many of these frequencies, whether you see it or not. That's why night vision works. It's why microwaves heat food. It's why medical imaging can look inside the body. The universe emits more light than we can ever see directly, but it's all energy, constantly exchanged. When you feel a breeze carrying warmth, or see sunlight slant through a window, you're interacting with layers of energy that have taken long paths to get there. The warmth came from friction in air molecules, from surface contact, from radiative heat. The light passed through clouds, bounced off particles, maybe refracted through glass. The processes are constant, but the outcomes shift depending on the materials, angles, and conditions involved. Nothing repeats exactly, but the rules stay the same. Even in places that seem cold or dim, energy is still flowing. The inside of a cave, the bottom of the ocean, the shadow behind a building, all of them contain molecules in motion, photons in flight, and exchanges happening out of sight. Energy doesn't require attention. It continues, whether noticed or not. It's easy to forget how active the world is at a basic level. Because heat and light are so familiar, they don't always feel remarkable. But if you stop and trace them, where they came from, what they're doing, where they're going, they open a door to understanding how connected everything really is. Every warm patch of air, every beam of light is part of a chain. You're part of it too. All of this motion, all of this heat, all of this light, they follow patterns, not just in how they move, but in where they tend to go over time. And the longer you watch anything energetic unfold, whether it's a cup of coffee cooling down or a galaxy spinning across billions of years, the more you notice something consistent. Energy doesn't stay concentrated. It spreads, it thins out, it disperses into forms that are harder to collect or reuse. This natural tendency for energy to move from more useful to less useful forms is what we call entropy. It's a word that gets used in a lot of contexts, sometimes casually, but in physics, entropy has a specific meaning. It's a measure of disorder. Or more precisely, it's a way of counting how many different ways a system can be arranged internally without changing what it looks like on the outside. The more arrangements available, the more random motion, the more mixed up options, the higher the entropy, and most systems left to themselves tend toward more of it. Imagine pouring cream into coffee. At first, the cream and the coffee are distinct. You can see the swirls. The cream is concentrated in a few places, but over time, without you needing to stir, the cream begins to spread. The sharp boundary fades. Eventually, the liquid becomes a uniform shade of brown. The molecules have mixed. The concentration has evened out. That final state has higher entropy. There are more ways for the molecules to be arranged and still look like blended coffee than there were when the cream was just beginning to enter the cup. The same goes for heat. If you place a hot object next to a cold one, the heat will flow from the warmer object to the cooler one until both are the same temperature. You'll never see the reverse happen on its own. A cold spoon doesn't spontaneously draw heat from a lukewarm drink and get hot while cooling the liquid. That's not because it's impossible in principle. It's just so incredibly unlikely, statistically, that you'll never witness it. There are vastly more ways for molecules to spread energy evenly than for them to all push it in one direction. This is the heart of the second law of thermodynamics. It tells us that the total entropy of a closed system, one with no outside input or loss, will either stay the same or increase. It won't decrease. Over time, things become more mixed, more spread out, more disordered at the microscopic level. That doesn't mean chaos in the everyday sense. It just means the energy becomes harder to gather and reuse. This is why no engine is perfectly efficient. Some energy always gets converted into heat that escapes into the environment. It's why buildings cool down in winter, why batteries run out, why ice melts, why sounds fade. Energy doesn't vanish, but some of it always becomes less useful, less focused. That's entropy in action, not as a dramatic collapse, but as a slow, steady drift toward equilibrium. Equilibrium is just a state where there's no more reason for energy to flow from one place to another. Everything has settled. The coffee and cream are mixed. The room and the air inside it are the same temperature. The battery is dead. The system has no gradients left. No highs or lows to move between. That state has high entropy. It's stable. not because nothing's happening, but because everything is equally spread. This isn't just about objects in a room, it applies to the universe as a whole. The early universe, right after the Big Bang, was extremely hot, dense, and uniform. That might sound like high entropy, but it was actually low. Everything was packed into a small space with little variation. As the universe expanded, energy began to spread out. Matter clumped into stars and galaxies, but overall the energy distribution became more complex, more dispersed. The entropy increased. It's increasing still. Stars burn fuel, releasing light and heat into space. That radiation carries energy away, spreading it across vast distances. Over billions of years, as more fuel is used up and more energy escapes into the background, the universe continues to drift toward a state where everything is more uniform, more spread out, higher in entropy. Eventually, far into the future, that process might leave the universe in a state of what's called heat death. Not dramatic, not fiery, but quiet. A condition where energy is so evenly distributed that no useful work can be done. No stars, no engines, just particles and low-temperature radiation, stretched thin across an enormous volume of space. It's not certain that it will end this way, but according to current models, it's one likely possibility. And it all comes from the same basic rule. Energy spreads. That might sound bleak, but it's not really. It's simply the shape of how systems evolve over time. And in the short term, in scales we live and work within, entropy isn't the enemy. It's what makes many things possible. The energy released by a burning log is due to chemical bonds moving toward more disordered arrangements. The cooling of your body after exercise is heat moving outward, equalizing. Even the digestion of food involves breaking complex molecules into simpler ones, releasing energy in the process. Those transformations depend on the system not staying too ordered. It's easy to misunderstand entropy as just decay, but that's not accurate. Entropy isn't destruction. It's transition. It's not a collapse into chaos. It's the natural result of energy following the path that gives it the most freedom. Left to itself, energy will take the route that allows the greatest number of internal movements. It doesn't stay boxed in. It spreads because that's what the math of the universe allows most easily. This is also why keeping things organized, in the human sense, requires constant effort. A clean room, a charged phone, a working refrigerator, they're all low entropy states, and they require energy to maintain. If you stop cleaning, charging, or powering, the systems trend toward disorder. It's not that they break because of some flaw. They break because holding them in a low entropy state takes work, and without that work, they return to a more probable configuration. That doesn't mean things can't improve. We constantly create order in small places by using energy that was previously stored. A plant turns sunlight into sugars, organizing molecules into new structures. A person builds a sand castle, turning chaotic grains into something specific. But in doing so, energy is spent, heat is released, calories are burned, light is absorbed. The local drop in entropy is balanced by a greater increase somewhere else. The system as a whole follows the rule, even if parts of it seem to move against the trend. Entropy is also tied to time. The reason we experience time as moving forward, not just as a mental sensation but as a physical reality, is closely connected to the fact that entropy increases. A spilled glass of water doesn't reassemble itself. A crumbled piece of paper doesn't unfold. These changes happen in one direction and not the other, because the forward direction allows for more microscopic arrangements. The math doesn't prevent the reverse, it just makes it so unlikely that we never see it happen. That's why time and entropy are often discussed together. You remember the past but not the future because the past was lower in entropy. Your brain records information by using energy to make changes, and those changes are themselves subject to the same drift. Memory requires structure, and structure requires energy. As energy spreads, the structures fade, and so does the sharpness of what you recall. Entropy isn't the reason we age, but it's one of the underlying influences. Cells accumulate errors, systems lose efficiency, molecules break down. Over time, maintaining low entropy states becomes harder. The energy is still there, but less of it is in forms we can easily use. The body, like every other physical system, shifts toward more probable arrangements, not all at once, not even steadily, but inevitably. None of this means we're powerless in the face of entropy. In fact, we live because of it. The sun shines because hydrogen fuses into helium, releasing energy in a high entropy reaction. That energy fuels photosynthesis, which feeds plants, which feed animals, which feed us. Our entire food chain is a cascade of entropy-generating processes, each one moving energy through steps we can benefit from. Life is not a rebellion against entropy. It's a clever use of it. Machines, organisms, weather systems, even ideas, all of them rely on inputs of energy to maintain structure, to resist the leveling out that entropy brings. The resistance doesn't violate the rule. It works within it. We create localized order using external energy, and in the process, the broader system becomes more disordered overall. That's not failure. That's participation in the larger pattern. So when you heat up a meal, or light a candle, or step outside into the sunlight, you're stepping into a story already in motion. You're watching energy move from focused to dispersed, from concentrated to shared. You're part of the process, not just observing it, but contributing to it. Every exhale, every movement, every bit of warmth around you is energy finding new places to go. It's easy to think of energy as something abstract or distant, something that belongs to stars, to laboratories, to theoretical equations. But that's not where most of us encounter it. The place where energy really shows up over and over again is in the everyday. You don't have to look far, just go through a typical day and you'll find energy shaping nearly everything you do, whether or not you're thinking about it. Start with waking up. If you're using an alarm clock or a phone, it had to be charged the night before. That power came from the grid. That grid is connected to a power plant, which could be running on coal or natural gas or water or wind or sunlight. Regardless of the source, the process began with some kind of energy being released or captured, converted into electricity, and sent through miles of cables just so your phone could light up at the right time. Even before you've stepped out of bed, energy is already involved. Your body has kept working all night, maintaining temperature, regulating your heartbeat, adjusting your position as you sleep. None of that happens passively. Your body draws from internal energy stores, the chemical energy you get from food. It's happening quietly but steadily. You're not charging up like a machine while plugged in. You're running constantly, even during rest. Getting up, stretching, walking across the room. These actions feel small, but they're powered by chemical reactions inside your muscles. Your cells are breaking down glucose molecules and converting that stored energy into usable fuel. Molecules like ATP, adenosine triphosphate, are acting as intermediaries, releasing bursts of energy when their bonds are broken. Each movement, no matter how small, is the result of tiny coordinated exchanges. Turning on the shower means tapping into another system. Water pressure comes from pumps and reservoirs, which require energy to maintain. If the water is hot, that heat had to come from somewhere. Maybe a gas-powered heater, maybe an electric one. Either way, energy was used to warm the water before it ever touched your skin. That warmth feels nice, but it also demonstrates how energy moves into and out of materials. The water doesn't create the heat, it carries it. Cooking breakfast adds more layers. Heating a pan transfers energy into the surface, which in turn transfers it to the food. That process, conduction, is just another form of molecular vibration, one material agitating another. If you're using a gas burner, you're releasing the chemical energy stored in fuel. If you're using an electric stove, the energy might have come from solar panels or a nuclear reactor. Either way, What looks like a simple meal is actually the final stage in a long chain of transformations. Then there's the food itself. The calories listed on a label aren't just numbers for diets, they're a measure of stored energy. That energy was originally captured by plants through photosynthesis. Sunlight hit leaves, and plants turned that light into sugar using carbon dioxide and water. Animals ate the plants. You ate the food. The chain is long, but each step is just another transfer. The original energy came from the sun. Everything since then has been repackaging. Even sitting at a desk staring at a screen is full of energy exchange. Your computer draws electricity. The screen emits light. The processor rearranges electric charges at high speed. The muscles in your neck, shoulders and eyes stay engaged, even if you're not conscious of the effort. Your brain is interpreting input, making decisions, sending signals. Focus takes work. So does comprehension. So does imagination. Every part of your home, from the thermostat to the refrigerator to the Wi-Fi router, is connected to a flow of energy. Appliances hum, blink, and adjust. Lights turn on and off. Clocks run. Fans spin. Each of those actions is minor, but together they create the rhythm of modern life. You're surrounded by devices that depend on continuous, structured energy input, and by systems that regulate that input to keep things stable. If you step outside, the energy flows continue. The warmth on your skin isn't just pleasant, it's infrared radiation arriving from 150 million kilometers away. The wind on your face is the result of pressure differences caused by the uneven heating of the Earth's surface. The sounds around you, footsteps, traffic, birds, are waves of kinetic energy moving through air molecules, eventually reaching your ears and triggering nerve signals. Transportation adds even more motion. Driving a car means burning fuel or draining a battery. That energy turns into kinetic motion, moving you, the vehicle, and everything inside it. Biking or walking draws directly from your body's chemical energy reserves. Public transportation depends on large-scale systems. Trains powered by electricity, buses fueled by combustion, all part of a massive web of energy infrastructure. Even things that feel inactive are full of motion. The clothes you wear are holding onto warmth. The pavement beneath your feet absorbs sunlight, stores heat, and slowly radiates it back. A puddle on the street evaporates over time, transferring water molecules into the air using ambient heat. The process is slow, but it's measurable. Given time, even the quietest parts of your environment will shift and change, because energy doesn't sit still. Interactions with other people are shaped by energy too. Smiling takes muscle movement. Talking involves breath, sound, motion. Eye contact depends on photons bouncing from one person to another. Thought, emotion, and attention are all powered by physical processes in the brain. Even empathy, that sense of understanding or resonance, is rooted in the activity of neurons. Each connection involves subtle movement and exchange. Energy flows through the more structured parts of your life as well. Every purchase, message, and appointment is tied to energy use. Digital communication relies on data centers powered by massive electrical inputs. Supply chains depend on trucks, ships, factories, and warehouses, all of which burn fuel, use machines, and require infrastructure. Behind every item you touch is a story told in kilowatt hours, in joules, in BTUs. The numbers are invisible, but the patterns are everywhere. You don't need to know the math to be part of it. Every time you charge a device, flick a switch, take a step, or heat something up, you're taking part in energy transformation. That's not just physics at work. It's how daily life unfolds. These are not exceptions. They are the rule. From breakfast to bedtime, the cycle continues without interruption. Even how you rest is shaped by energy. When you lie down and relax, you're still generating heat. Your body adjusts its internal rhythms. Your brain rebalances chemical levels. If you fall asleep, the patterns change again. into stages marked by electrical shifts, brainwave patterns, memory consolidation, and muscle repair. None of it happens for free. Rest is still an energy-driven process. It's just a different kind of work. The clothes you wash, the house you heat, the emails you send, they're all part of systems built on movement. That movement is measured, managed, and monitored in ways we usually don't think about. But the principle behind them doesn't change. It's all energy. All of it obeys the same laws. All of it transforms, spreads, and continues. Even waste is part of the equation. The heat your laptop gives off, the sound your fridge makes, the exhaust from a car, these are forms of energy that aren't doing useful work anymore, but they haven't disappeared. They've just moved down the chain, contributing to the overall flow. You don't have to follow each particle to know that the cycle continues. The more closely you pay attention, the more visible it becomes. Not in a dramatic way, but in subtle details. The way sunlight shifts across a wall, the sound of air moving through vents, the warmth left behind on a chair, small traces of the larger pattern, all of them telling you the same thing, that nothing is truly still and everything is part of a process. You're in that process too. You're not a separate observer, you're a participant. Whether you're active or still, alert or at rest, you're made of systems that turn energy into motion, into thought, into action. The choices you make, what to eat, when to move, how to sleep, shape how that energy is used. But the rules stay the same. Input becomes output, stored becomes spent, the cycle repeats. So far, most of the energy you've noticed in daily life has taken familiar forms: heat, light, motion, sound. But inside your own body, there's another kind that plays an even more critical role, one that's harder to see or feel directly: electrical energy. It's not the kind that runs through wires in your house. It doesn't come in sparks or shocks, at least not usually. But your body depends on electricity in deeply structured ways. The signals that let you move your fingers, form a thought, take a breath. All of them rely on electrical impulses. Without them, none of it would work. The idea might sound surprising at first. We don't think of ourselves as electric. We think of ourselves as flesh and blood, muscles and bones. But the coordination behind all of that is electrical. Your nervous system is, at its core, an electrical communication network. It doesn't look like one. It's made of soft tissues, not wires. But it works on the same basic principle. A signal needs to go from one place to another. Energy is the carrier. The cells that handle this work are neurons. There are billions of them throughout your brain, spine, and peripheral nerves. Each one is specialized to carry tiny controlled bursts of electrical charge. Not huge, not dangerous, just enough to pass information. The way they do it is surprisingly elegant. At rest, each neuron maintains a voltage difference between the inside and outside of its membrane. That difference exists because of how ions, charged particles like sodium and potassium, are distributed across the membrane. The cell works to keep more of certain ions on one side than the other, building up potential. That potential energy is electrical in nature. It's like a tiny charged spring waiting to release. When the neuron is triggered by a chemical signal, a stretch, a light touch, that potential is suddenly released. Ion channels open, allowing charged particles to flow across the membrane. That flow is what creates the electrical pulse. It moves along the length of the neuron, down its axon like a tiny wave. When it reaches the end, it usually triggers the release of neurotransmitters, chemical messengers that pass the signal to the next cell. The whole process happens incredibly fast. Nerve impulses can travel anywhere from a few centimeters to over 100 meters per second, depending on the type of neuron. That's how you can touch a hot surface and pull your hand away almost immediately. Your body registers, processes, and reacts to the sensation in fractions of a second. But even slower processes like thinking or dreaming are built from the same kind of electrical flow. The patterns in your brain, the ones that define attention, emotion, memory, are coordinated through electrical rhythms. When scientists measure brain activity, what they're detecting are these rhythms, waves of electrical potential shifting across neural networks. That's what an EEG shows, not your thoughts themselves, but the underlying oscillations. These waves have different frequencies depending on your state. High-frequency beta waves when you're alert and focused, slower alpha or theta waves when you're relaxed, even slower delta waves when you're in deep sleep. Each of these states is a pattern of energy moving across the brain, the body electric at rest and in motion. Electricity in your body doesn't just stay in the nervous system, your heart uses it too. The heartbeat is controlled by a tiny group of cells in the right atrium, known as the sinoatrial node. These cells act as a natural pacemaker, generating regular electrical impulses that cause the heart muscles to contract in rhythm. That pulse travels through specialized pathways, ensuring the chambers of the heart beat in the right sequence. When doctors measure your heart's electrical activity, they use an electrocardiogram, ECG or EKG. The spikes and waves you see on the printout are visual representations of those electrical signals. Each bump corresponds to a different part of the heartbeat: the initial impulse, the contraction, the recovery. It's a clean, readable version of energy flowing through a living system. You might not feel this electricity directly, but it governs what your body does second by second. Every blink, every swallow, every adjustment in posture involves motor neurons firing. Every sensation, from pressure to pain to temperature, starts with a signal picked up by specialized cells and translated into voltage changes. Your brain interprets those signals not as electric pulses, but as experience. Even balance and coordination rely on this. When you stand upright, your muscles are constantly adjusting, based on signals from your inner ear, your joints, your eyes. Those signals move as fast as possible because delays would mean instability. The system only works because the communication is electric. But electricity isn't just used for movement and perception. It's essential to chemistry too. The movement of ions, positive and negative charges, drives countless reactions in cells. Every time a muscle contracts, it starts with a flood of calcium ions into a fiber. That ion movement allows the proteins in the muscle to change shape and generate force. The same thing is true for digestion, for breathing, for healing. Cells use electric potential to manage what comes in and out of their membranes. They store gradients, little imbalances in charge, and use those gradients to power pumps, transport nutrients, build molecules. What feels like biology is, at its foundation, electrical and energetic. The molecules you digest for energy, carbohydrates, fats, proteins, eventually get broken down in mitochondria, the organelles often called the powerhouses of the cell. These structures use a process called oxidative phosphorylation to produce ATP, but the heart of that process is electrochemical. As electrons move along a chain of proteins, they create a proton gradient, another imbalance of charge. That gradient drives a tiny rotary motor, an enzyme called ATP synthase, that assembles ATP molecules. It's not metaphorical, it's an actual rotating machine, powered by electric imbalance. That's what your life runs on. Tiny engines turning inside nearly every cell, using electricity to manufacture chemical energy. The electrical potential is set up by eating, breathing, breaking things down. But the final step is rotation. It's movement. It's energy and motion, turned into structure. Even when cells die, the final moments involve electrical changes. When a neuron shuts down or when a heart stops, it's not just the loss of function, it's a collapse of gradients, a release of stored charge. The balance is lost. Energy, which was held carefully in arrangements, spreads. As always, it doesn't disappear, but it leaves the structure that once held it. That electrical side of life isn't something we usually think about. It doesn't feel electric. There's no sound, no flash, but it's always there. Quiet signals travelling from place to place, voltage patterns unfolding, the steady rhythm of charge flowing where it needs to go. The body doesn't need to be conscious of it. It just works. You're not just using electricity when you plug something in. You are electricity in a very literal sense. You're a system of organized charge, managing gradients, running impulses, keeping rhythm. Your body stores, generates, and spends energy constantly, using both chemical and electrical pathways to keep everything aligned. There's no need to design it. It's built into the physics. And while it's easy to separate ourselves from the rest of the world, to think of electricity and power lines as different from what's in our cells, it's the same basic idea. Charge, movement, gradient, flow. Whether it's turning on a light or taking a breath, the energy comes from differences. Places where something can move from higher to lower, carrying a bit of power as it goes. That movement once started continues, just like the electricity in your brain when you form a memory. Just like the pulse that moves your muscles when you lift your hand. Just like the signal that travels down your spine when you speak or smile or shift your weight. It's happening constantly, steadily, invisibly. Not loud, not bright, but unmistakably alive. You might think of sleep as a kind of pause, a break from activity, a shutting down of systems that ran all day, and on the surface that makes sense. Muscles go still, awareness fades, eyes close, the body stops moving in the way it does when you're awake. But underneath that quiet, sleep is anything but still. It's not a shutdown, it's a reorganization. The process starts before you even realize it's happening. As you lie down and let your thoughts slow, your brain begins shifting gears. The electrical activity in your cortex drops from high-frequency patterns, the ones that dominate during focused attention, into slower, broader waves. These changes aren't accidental. They're coordinated, guided by structures deep in the brain that regulate sleep onset. One of those structures is the suprachiasmatic nucleus, part of the hypothalamus. It helps regulate circadian rhythms, the natural 24-hour cycle that governs sleep and wakefulness. It responds to light levels, temperature, and chemical signals. As evening sets in, it sends instructions that shift the body toward rest, lowering core temperature, changing hormone levels, easing the body out of high alert mode. Melatonin, one of the hormones involved, rises in the bloodstream, heart rate slows, breathing deepens, muscles relax. But none of this is passive. Each change requires energy. Cells adjust. Blood vessels expand or contract. Electrical activity in the brain doesn't go dark. It takes on a different shape. You don't drift into one long continuous state. Sleep happens in cycles, each lasting around 90 minutes. During those cycles, your brain moves through multiple stages. At first, the activity slows further. Light sleep, where the mind begins to detach from the surrounding world. Then deeper stages follow. In those moments, neurons fire in synchrony, creating slow waves of voltage across the cortex. It's a highly organized kind of stillness, not silence, but pattern. In this deep sleep, the body is busy with repair. Growth hormone is released, cells regenerate. The immune system becomes more active. The brain starts filtering through recent experiences, tagging some for storage, discarding others. It's not conscious, but it's not quiet either. After a while, something shifts again. Brain activity becomes more varied, more irregular. Muscles stay mostly still, but the eyes begin to move behind closed lids. This is REM sleep, rapid eye movement, and it's where dreams most often happen. During REM, parts of the brain become as active as they are during waking hours. The visual cortex lights up, memory centers engage, emotions surface. It's not random firing. It's a kind of internal rehearsal, a reshuffling of information and experience. Your muscles remain paralyzed during REM, not as a failure, but as a safety feature. The body keeps itself from acting out the contents of your dreams, but everything else is in motion. The heart beats irregularly. Breathing becomes shallower, then deeper again. Electrical waves ripple through the brain. neurotransmitters shift. Then the cycle begins again. Back into light sleep, into deeper stages, into REM. Most people move through 4 to 6 of these loops in a full night, with each REM period growing longer as morning approaches. It's not a flat line, it's a curve, a rhythm, and each phase plays a role. Sleep deprivation doesn't just make you tired, it interrupts these cycles. Without them, the body doesn't get the time it needs to repair cells, regulate metabolism, balance mood, process memory. The mind becomes less coordinated, the immune system weakens, blood sugar control falters, attention slips. These aren't side effects. They're the consequences of skipping necessary energy exchanges. Even the act of waking up isn't a simple switch. It's a gradual reversal. Hormone levels shift, core temperature rises, electrical activity in the brain ramps up again, from low-frequency waves to more irregular, higher-frequency patterns. Muscles respond to signals again. Sensory systems reboot. Consciousness rebuilds layer by layer. Your dreams, even the ones you forget, are part of that rebuilding. They draw from stored images, emotions, fragments of memory. The brain uses them to test associations, rehearse reactions, explore possibilities. You don't control the content, but your mind is actively constructing it from real material. Even nonsense has roots. The process uses energy, reorganizes connections, fine-tunes circuits. If you've ever woken up feeling more clear-headed than when you went to bed, that clarity didn't come from stopping. It came from movement, from coordinated, regulated, purpose-driven activity inside the brain and body. Sleep didn't quiet everything, it rerouted the traffic. Sleep also influences how your body stores and uses energy. During deep sleep, the body becomes more efficient at regulating blood glucose. Hunger-related hormones are reset. The balance between leptin and ghrelin, which influence appetite, is recalibrated. Without enough sleep, that balance is disrupted. You're more likely to feel hungry, less likely to feel satisfied. That's not willpower, it's chemistry. Muscle repair happens at night too. Small tears from daily activity are patched. Proteins are rebuilt. If you're physically active during the day, sleep becomes even more critical for recovery. The energy that went into motion during daylight hours is used to rebuild tissue at night. It's the other half of the process, and it's just as energetic. It's just less visible. Even learning depends on sleep. During REM, and to some extent in deep non-REM phases, the brain replays neural activity from earlier in the day. The patterns of motion, the firing of pathways involved in new tasks, are repeated. It's like reinforcing a trail by walking it again. If you're studying something or practicing a new skill, a full night of sleep helps consolidate what you've taken in. You're not reviewing it consciously. But the circuitry is being stabilized. None of this is quiet in the energetic sense. Brain scans during REM look almost indistinguishable from those taken during waking thought. The differences in input and output. Your body is disconnected from the environment. You're not receiving sensory input or producing external motion. But inside the system, the activity hasn't stopped. It's shifted to internal use. Temperature regulation continues too. Your body adjusts to changes in room temperature. Blood flow is rerouted to preserve warmth or shed excess heat. The metabolic rate drops slightly but doesn't halt. The brain, despite representing only a small percentage of body weight, consumes a disproportionate amount of the body's total energy, and that demand continues through the night. Even when you're dreaming about flying or falling or floating, none of it is still. Every image, every emotion, every flicker of light behind your eyelids is being assembled in real time from energy moving across networks. Neurotransmitters are firing, cortical regions are activating and synchronizing. The stillness is external. Internally, it's closer to a controlled storm. People sometimes describe deep rest as feeling recharged, like a battery that's filled back up. That's a fair comparison, but not a literal one. Sleep doesn't give you more energy from the outside. It rebalances the energy you already have. It prioritizes, repairs, streamlines, clears out build-up. It lets systems reset so that the next day's input can be handled more efficiently. You're not getting more energy. You're improving the conditions under which you use it. The body's electrical systems don't shut down at night. They shift into different cycles. The motion never stops. It just reconfigures. And the result, when it works well, is that you wake up not just rested, but aligned. The rhythms of your body and brain have recalibrated to match each other again. The electric signals are moving smoothly, and you step back into the day with systems already humming. All the energy that moves through your body, through your food, through the light on your skin, can be traced back to a much larger source. A fire that's been burning for billions of years, steady and unrelenting. It doesn't burn like a campfire or a candle. It doesn't use oxygen, but it's the reason you exist at all. That fire is the sun. From 150 million kilometers away, the sun sends a constant stream of energy across space. It arrives in the form of light and heat, crossing empty vacuum without slowing down. That energy warms the earth, drives the weather, feeds the plants, stirs the oceans, regulates sleep cycles, powers solar panels. Everything that grows or breathes is responding to what the sun produces. At its core, the sun is a nuclear fusion reactor. But unlike a man-made reactor, it doesn't sit in a containment chamber. It holds itself together with gravity. The pull of its own mass is strong enough to press the atoms at its center into a dense hot plasma, hot enough for fusion to occur. The numbers are extreme. At the center of the sun, temperatures reach around 15 million degrees Celsius. The pressure is so high that hydrogen atoms, the lightest and most common in the universe, are forced close enough to fuse into helium. That fusion process releases energy, a lot of it. Every second, the sun converts about 600 million tons of hydrogen into helium. The difference in mass, a few million tons, is released as energy, following Einstein's equation, E equals mc squared. That mass is gone, transformed into pure energy that moves outward from the core through layers of plasma, finally escaping from the surface as light and heat. But the light you see today wasn't just created a moment ago. The photons released in the core don't exit the sun instantly. They bounce around inside it for tens of thousands of years, scattering through dense layers of gas before finally reaching the surface. Only then are they free to travel the vacuum of space. Once they leave the surface, the trip to Earth takes just over 8 minutes. That means when you feel sunlight on your skin, you're interacting with energy that started its journey before human civilization even existed. The particles themselves are recent, but the process that created them began in the distant past, through movements so dense and chaotic that no single path can be traced. And the sun isn't unique. It's one of hundreds of billions of stars in the galaxy, each with its own structure, its own rate of fusion, its own lifespan. Some are smaller and cooler, some are massive and burn through their fuel quickly. But the core idea is the same. Gravity creates pressure, pressure creates fusion, and fusion releases energy. Not all stars shine with the same intensity. Their colour tells you something about their temperature. Blue stars are hotter, emitting more energy in the higher frequency part of the spectrum. Red stars are cooler, burning more slowly. Yellow stars, like our sun, fall somewhere in the middle, a balance of brightness and stability. That stability matters. It's what allowed Earth to develop over long periods without being frozen or scorched. It's what gives life time to evolve. Some of the energy released by stars never reaches planets. It drifts through space, intercepted by dust, gas, or nothing at all. But the fraction that does reach a surface can have enormous effects. A planet tilted slightly on its axis will experience seasons. A slight change in distance from its star can mean ice ages or deserts. The energy output from the sun shapes more than just temperature. It influences atmosphere, magnetic fields, even chemistry. Photosynthesis is one of the most direct examples. Plants capture sunlight using pigments like chlorophyll. That light excites electrons in the pigment molecules, setting off a chain reaction that splits water, absorbs carbon dioxide, and creates sugars. Those sugars store the energy from the sun in chemical form. Every time you eat something that grew in sunlight, you're using energy that started in the core of a star. Even the fossil fuels that power machines, coal, oil, natural gas, are long-term storage of solar energy. Ancient plants, buried and compressed over millions of years, became carbon-rich materials. When you burn them, you're releasing energy that was captured in sunlight before there were mammals. It's not new energy, it's a withdrawal from an old deposit. That's true for wind and waves as well. Winds form because of temperature differences, air moving from high to low pressure driven by solar heating. Waves build from wind pushing on the ocean's surface. Even the energy stored in the movement of tides, while mostly influenced by the moon's gravity, depends in part on solar effects. Energy passes through layers, reshaping forms, changing carriers. But it originates from the same furnace. Stars don't burn forever. Fusion uses up fuel. In the case of the sun, it has enough hydrogen to keep shining for another 5 billion years or so. After that, it will expand, shift into a red giant, shed its outer layers, and eventually collapse into a white dwarf. The energy output will drop. The fire will fade. But for now, it remains steady. A stable engine in the sky, producing more energy each second than humanity has ever used in its entire history. From the surface of Earth, it can be hard to grasp the scale. The sun takes up only a small part of the sky. It rises and sets, seemingly consistent, seemingly simple. But that consistency hides the scale of what's happening. A nuclear reaction held in place by gravity, continuing for billions of years, pushing out energy in all directions without pause. The sunlight that streams through your window isn't abstract. It's photons, tiny packets of energy, arriving one after another. They can be absorbed, reflected, refracted. They can warm a surface, trigger a chemical change, create shadows, power reactions. You don't have to see the process to be shaped by it. The energy arrives regardless. At night, when the sun is out of view, the fire hasn't stopped. It's still sending out light. The earth has simply turned away. In that darkness, the sky reveals more fires. Distant stars, faint but steady. Their light takes much longer to reach us. Sometimes decades, sometimes centuries, sometimes longer than the entire history of human writing. But it keeps moving. The photons keep arriving. The energy keeps flowing. And not all that light stays visible. Some of it becomes heat in the atmosphere. Some is captured in leaves. Some reflects off snow or sea or glass. It joins the system. It's added to the planet's budget. Even if only a fraction is absorbed, it's enough to power climates, ecosystems, machines, and metabolisms. You don't need much of it, just a sliver, for the effects to be enormous. Energy from stars isn't optional, it's fundamental. It's the background condition that allows everything else to happen. Life didn't just emerge on a warm planet by accident. The heat, the light, the rotation, the chemistry, all of it depends on the ongoing delivery of stellar energy. Without it, molecules would stay frozen, reactions would stall, nothing would grow, move, think, or change. And so the fire continues, even if you're not looking, even when it's cloudy, even when it's winter. The photons still come, the energy still arrives, and the systems built to use it, leaves, skin, sensors, cells, continue their work, quietly, steadily, without pause. Light, once it leaves a star, doesn't stay in one place. It moves, fast, constant, uninterrupted. In a vacuum, it travels at about 300,000 kilometers per second. That speed doesn't change. It doesn't matter where it's going or what it's made of. It moves until it hits something, and when it does, what happens next depends entirely on what it hits. Some materials absorb it, Some reflect it, some bend it, some let it pass through. These different interactions are the reason you see colour, depth, shape, and texture. The world doesn't emit light on its own. It's mostly visible because light bounces off it. That bouncing, that scattering and reflecting, is how vision works. You're not seeing objects directly. You're seeing the photons that bounced off them and into your eyes. A surface that reflects more light appears brighter. A surface that absorbs more looks darker. The way the light bounces also tells you something about the surface. A smooth surface reflects light in predictable angles. That's why you can see your face in a mirror. A rough surface scatters light in multiple directions. That's why a wall looks matte or soft. The texture is real, but the appearance is shaped by how light interacts with it. This is why shadows exist. When an object blocks a stream of light, the light can't continue in a straight line. The area behind the object doesn't get illuminated. That absence creates a shadow. It's not a thing by itself. It's just a place where the light didn't reach. But even shadows aren't completely still. Light bends slightly around edges, a behaviour called diffraction. It also scatters off dust, air, or surfaces. That's why shadows have soft edges in some cases. It's not that the light stops completely, it's just thinned out. The darker the shadow, the less stray light is reaching it. But unless you're in a perfectly controlled environment, total darkness is rare. The sharpness of a shadow depends on the size of the light source and the distance between the object and the surface. A small focused light will create a clear, sharp shadow. A large, diffuse light, like the sun on a cloudy day, creates a blurrier one. The softness or sharpness is just geometry. It's the outline of where photons could and couldn't go. Sometimes shadows can even have more than one edge. This happens when multiple light sources are present. You've probably seen it. Overlapping shadows in a room with both ceiling lights and a lamp. Each light casts its own version of the obstruction, slightly offset from the others. It's not a trick. It's just overlapping paths of light and dark, adding or cancelling depending on where they land. And light isn't limited to what you can see. The visible spectrum is only a narrow band of electromagnetic radiation. Below that are infrared and radio waves, longer wavelengths. Above are ultraviolet X-rays and gamma rays, shorter, more energetic ones. They all move at the same speed in a vacuum. They all behave according to the same basic principles. But your eyes only detect the narrow range from roughly 400 to 700 nanometers in wavelength. That's what we call visible light. Infrared light, just beyond red, carries less energy per photon. It's often experienced as heat. You can't see it, but you can feel it, especially from warm objects. That's how thermal cameras work. They detect infrared radiation and turn it into a visible image. On the other end, ultraviolet light, just beyond violet, carries more energy. You can't see it either, but it can cause sunburns or help the body produce vitamin D. These invisible forms of light interact with matter just as much as visible light does, sometimes more. Light also refracts, bends, when it moves from one medium to another. That's why a straw looks like it's bending when placed in a glass of water. The light moves slower in water than in air. That change in speed shifts its direction. Lenses rely on this behaviour. So do glasses, microscopes, cameras. The shape of the lens determines how light is bent, and that bending can bring things into focus. Transparent materials allow light to pass through, but not all in the same way. Some let it move through cleanly, like clear glass. Others scatter the light slightly, like frosted glass or mist. The difference isn't in the light, but in the structure of the material. Irregularities scatter photons in random directions. That's why you can see light through a shower curtain, but not details. And then there's colour. It's not something objects produce on their own. It's the result of which wavelengths of light are absorbed and which are reflected. A red apple looks red because it reflects red wavelengths more than others. A leaf looks green because it reflects green more than it absorbs. Under different lighting, the same object can look different, because the incoming spectrum has changed. White light, like sunlight, contains a broad mix of wavelengths. When it passes through a prism, the different wavelengths bend at slightly different angles, separating into a spectrum. That's what creates a rainbow. The colours were already there. The prism just spread them out. You can create similar effects with mist, glass, or thin films. A soap bubble shows colour patterns because of interference. Some light waves reflect off the outer surface, others off the inner, and the waves combine or cancel depending on their path lengths. That's why the colours shift as the bubble moves. It's the thickness of the film that's changing, not the light itself. Light also interferes with itself. Shine it through two narrow slits, and you'll get a pattern of bright and dark bands, even if you send the photons one at a time. The light waves overlap and combine. Where the crests of the waves match, they amplify. Where they cancel, you get darkness. This behaviour, wave interference, is one of the ways we know light isn't just a stream of particles, but it is also a stream of particles. Photons carry energy and momentum. They have no mass, but they behave as if they're packets, discrete, countable units. This dual behaviour, wave and particle, is part of what makes light strange. Depending on how you measure it, it shows one aspect or the other. It's not just one thing, it's both, depending on context. When light hits matter, it can do many things. It can be absorbed and converted into heat. It can excite electrons and cause chemical changes. It can reflect and bounce. It can pass through. Which of these things happens depends on the structure of the material and the energy of the photons. In your eye, light triggers photoreceptor cells, rods and cones, that respond to different wavelengths. Those cells convert light into electrical signals. The brain receives those signals and builds an image. What you see is not the light itself, but the interpretation your brain makes of those inputs. Vision is a reconstruction. Light carries the data, but you do the rendering. And the absence of light, that's darkness. Not a substance, just a condition where fewer photons are arriving. It's the default when nothing's emitting or reflecting. But even in darkness, light can be found if you know where to look. Infrared cameras, long exposure photography, radio telescopes, they reveal what's still there, just outside the narrow slice we can perceive. Shadows are a reminder of this. They show where light didn't reach, but not because light is missing from the world, just because something was in the way. They're outlines of blocked paths, and they're always changing. As the light source moves, like the sun across the sky, the shadows shift. Their length, shape, and direction evolve with the position of the light. You can tell the time by them, if you know how to read the angles. All of this, reflection, refraction, absorption, scattering, is motion, not just of light, but of energy. Light arrives with energy. What happens next is always a transfer. Some of it becomes warmth, some of it becomes signal, some is stored, some is redirected, but none of it disappears. You see the light, you feel the heat, you notice the shadows. But what you're really watching is energy moving through space, interacting with matter, following rules that apply from the smallest scale to the largest. Energy at its core is what makes change possible. Nothing shifts, grows, moves, or decays without it. It's not just a background condition, it's the enabling factor, the reason anything alters from one state to another. When you look at a leaf falling from a tree, or ice melting in a glass, or metal heating up under a flame, what you're watching is energy at work. Not in a metaphorical way, in a physical, measurable one. The atoms and molecules that make up those materials are shifting in response to input. Bonds are breaking or forming. Positions are rearranging. The result is change. A simple example is phase change, when a substance moves from one state of matter to another, solid to liquid, liquid to gas, and so on. Those shifts require energy. Not to add mass, not to alter the chemical identity of the material, but to change how its particles behave. Take water. Turning ice into liquid water takes energy, specifically heat. That heat doesn't make the molecules heavier or faster in a direct sense. It breaks the structured bonds holding the water molecules in place as a solid. Once those bonds are loosened, the molecules can move more freely, and the ice becomes a liquid. The temperature stays steady during that change, even as energy continues to flow in. That's because the energy isn't going into making the molecules hotter, it's going into changing the arrangement. That kind of energy is called latent heat, the hidden energy required for a phase change. You can't see it as a temperature spike, but it's there, it's necessary. The same thing happens when liquid water turns to steam. More energy is needed to separate the molecules further, overcoming attractive forces. The system doesn't just heat up, it reorganizes, melting, boiling, evaporating, condensing, freezing. All of them are transitions that depend on energy. The direction of energy flow determines which change occurs. Add energy and particles move more freely. Remove it and they slow down and reattach. The change seems simple, but the underlying motion is constant. This applies far beyond simple substances. In chemical reactions, energy is involved in breaking and forming bonds. Some reactions release energy, exothermic ones, and others require energy input, endothermic ones. That's why certain processes happen on their own, while others need a push. When a log burns, it releases stored chemical energy. The bonds between carbon and hydrogen atoms are rearranged in the presence of oxygen. The new molecules, mostly carbon dioxide and water, have lower chemical potential energy. The excess is released as heat and light. That energy had been stored in the wood since the tree formed it, using sunlight through photosynthesis. So the fire is just a delayed transfer, solar energy, captured, stored, and finally released in a different form. The reverse process, building complex molecules from simpler ones, takes energy. Plants do this with sunlight. Human-made factories do it with electricity or combustion. The act of building anything chemically or physically requires energy input to overcome resistance, to hold structure, to maintain order against the natural drift toward disorder. That same logic applies to biological change. Growth, healing, learning, even aging, all require or involve energy. Your body doesn't just passively increase in size or develop new structures. It draws on the chemical energy in food to build proteins, replicate cells, form tissues. When you recover from an injury, energy is spent rebuilding what was damaged. When you learn something new, neurons adjust their connections, a process that takes both chemical and electrical energy. Even decay is energetic, breaking down organic matter, oxidizing metal, degrading materials. All of it involves movement at the molecular level. Energy isn't just present during construction, it's involved in dismantling too. The structure held by bonds must be undone. That undoing isn't a lack of energy. It's the result of energy moving from one place to another, making old structures less likely to hold. Mechanical changes, like bending, stretching, or breaking, also depend on energy. When you bend a piece of metal, you're forcing its internal structure to rearrange. The energy you apply doesn't just vanish. Some is stored, some becomes heat, some may result in permanent deformation. The shape is different, but the energy accounts for the difference. On larger scales, these same rules apply. The erosion of a mountain, the shifting of tectonic plates, the formation of rivers, all are examples of energy reshaping matter. The energy may come from gravity, from the heat of Earth's interior, from solar radiation, from chemical reactions. But the pattern is the same. Matter responds to energy by changing form. Even memory, not just in brains but in physical systems, is a record of change. A magnet stores data by aligning tiny regions of material. A flash drive does it with electrical charges. A notebook stores it in the position of ink on paper. Each version is a changed state, one that took energy to create, and one that can be altered again with more energy. Energy doesn't just allow change, it leaves evidence of it. A melted candle, a burned-out light bulb, a faded photo, these are not passive outcomes. They're physical records of energy interacting with materials over time. The colour faded because light broke down chemical bonds. The bulb burned out because the filament evaporated due to heat. The candle melted because thermal energy rearranged the wax. Even the weather is full of these changes. Clouds form when water vapour condenses. That condensation releases latent heat into the atmosphere. Storms build when pressure differences create wind. Lightning discharges electrical energy built up in charged layers of cloud. Rain alters the surface of the land. Every shift from a light breeze to a hurricane is the result of energy differentials trying to balance out. The flow of time, in many ways, is tied to change, and change, by definition, requires energy. That's why a completely inert system, perfectly isolated, no energy transfers, no motion, wouldn't evolve. It wouldn't age. It wouldn't decay. It wouldn't remember. In theory, it would stay the same forever. But in practice, no system is completely closed. Even in deep space, background radiation provides a whisper of energy. This is why energy accounting matters. Physicists often keep track of how much energy is in each form: kinetic, potential, thermal, chemical. Not because the energy disappears, but because it moves. If something changes, the energy must have gone somewhere. Tracking that movement helps explain not just what happened, but how and why. Nothing changes without it. Not the small things, like a grain of salt dissolving in water, and not the vast ones, like a galaxy slowly stretching apart. The cause is energy, and the effect is difference. If a system looks different over time, it used or released energy in the process. That's the core link between energy and change. There are still different ways to harness it. Some changes are intentional, designed by humans for a specific purpose. Others are spontaneous, driven by natural gradients. But the rules stay the same. Energy can be stored, released, transferred, converted, but not created from nothing, or destroyed into nothing. Every change leaves a trail. Every transformation is a result of input and output. That's what makes energy central to every field of science. Not just physics or chemistry, but biology, geology, engineering, astronomy. If a system evolves, if it responds, if it alters in any way, energy is involved. You don't need to understand every detail to observe the results. The signs are visible, the pattern holds, and so the world keeps changing not at random but according to energy's guidance. Rain erodes stone, seeds become trees, circuits carry currents, muscles heal, ice melts, engines run, brains remember. Change isn't just something that happens, it's something that energy makes possible, again and again without pause. Sound feels like something we hear, but it's really something we're inside of. It's not a thing, not a substance, it's motion. Vibrations moving through air, water, solids. Each one a transfer of energy from one particle to the next. Without that movement, there's no sound. And without energy, there's no movement. It starts with a disturbance, something pushing on its surroundings. A hand claps, a string vibrates, a door slams. That push compresses the air in one spot, increasing pressure. That pressure spreads outward, like ripples from a stone dropped in water. But instead of ripples on a surface, it's pulses in a three-dimensional medium. Regions of compression followed by regions of rarefaction, molecules squeezed together, then pulled apart. These fluctuations move away from the source in all directions. That's what sound is, a longitudinal wave of pressure variations moving through a medium. Your ears don't pick up the pressure itself. They respond to the mechanical effect it has on your eardrum. As the pressure rises and falls, your eardrum moves back and forth. That motion is passed through tiny bones in your middle ear, the smallest bones in your body, which amplify and transmit it to the cochlea, a fluid-filled spiral in the inner ear. Inside that structure, hair cells detect the movement and convert it into electrical signals. Your brain reads those signals as sound. What you perceive, a voice, a note, a footstep, is your interpretation of those signals. But the signals are built from motion, vibrating air, tiny movements at the molecular level. Each sound you hear is energy in transit, shaped by its source and the path it takes. Loudness depends on amplitude, how much the air is pushed or pulled. The greater the displacement, the more pressure difference there is, and the louder the sound feels. Frequency determines pitch, how fast the waves are arriving. High-pitched sounds have waves arriving more frequently. Low-pitched ones arrive less often. The human ear can typically detect frequencies from about 20 Hz to 20,000 Hz. That means 20 to 20,000 pressure cycles per second. But sound isn't only something you hear, it's also something you feel. Very low frequencies, below the threshold of hearing, can cause vibrations you register in your body rather than your ears. That's what gives bass notes their physical presence. Subwoofers aren't just about volume. They move enough air to make sound tactile. Energy moves differently through different media. In air, sound travels at about 343 meters per second. In water, it's faster, around 1,180 meters per second. In steel, faster still, over 5,000 meters per second. The density and elasticity of the medium determine how quickly the wave can propagate. That's why underwater communication uses sonar, and why knocking on a metal pipe sounds sharper than tapping on wood. The material changes how the energy moves, but sound also loses energy as it travels. Some is absorbed by the medium, some is scattered, some reflects. That's why voices sound softer at a distance. It's not just about volume. The energy of the wave is being shared, lost, transformed. The further it goes, the less of it reaches you. Echoes happen when sound reflects back from a surface, a wall, a cliff, a building. If the surface is smooth and far enough away, the returning wave is heard as a distinct repeat. If the surface is closer or more irregular, the reflected waves blend with the original, creating reverb instead. The texture of a space is shaped by how sound energy behaves inside it. That's also how rooms are designed for specific sound experiences. A concert hall uses materials that reflect and diffuse sound to enhance clarity and richness. A recording studio uses absorption to minimize unwanted echoes. Even the shape of the room, its dimensions, its corners, affects how energy bounces, overlaps, or fades. In open air, sound spreads in all directions unless directed. That's why yelling in a field sounds different from yelling in a stairwell. In a small, hard space, the sound reflects back and layers on itself. In a large, soft space, much of the energy is absorbed or lost. Speech is one of the most familiar uses of sound energy. Air from the lungs is pushed through the vocal cords, which vibrate to create a fundamental tone. That tone is shaped by the position of the tongue, lips, and jaw. The result is a complex waveform, not just a single frequency, but a rich set of harmonics. When you talk, you're directing sound energy through controlled physical motion, and when you listen, your brain decodes those vibrations into meaning. Music builds on the same principles. Instruments create vibrations in different ways: plucked strings, struck surfaces, vibrating air columns, but all of them shape the flow of energy into patterns we find recognizable or expressive. Harmony, rhythm, timbre. These are all built from variations in how energy moves through time and space. But sound doesn't always come from intention. Natural systems produce it constantly. Wind moving through trees creates complex, shifting frequencies. Thunder results from the sudden expansion of air around a lightning bolt. Rain hitting a surface produces a wide, overlapping range of impact sounds. Animal calls, tectonic shifts, the hum of electricity and wires All are variations of pressure moving through material, and then there's silence, or at least the idea of it. In practice, complete silence is rare. Even in the quietest place there's usually something: the hum of blood in your ears, the creak of floorboards, distant traffic, your own breath. What we call silence is often just the absence of loud or distinct sound. But even then, energy is still moving. The room may have residual vibration. Air molecules are still in motion. Nothing is truly still. Some research labs have built anechoic chambers, rooms designed to eliminate as much sound reflection as possible. Inside them, most people can hear their heartbeat, the movement of joints, even the flow of saliva. The silence doesn't feel empty. It feels overwhelming because your body is still producing sound. The absence of external noise reveals internal energy. There's also sound we can't hear: ultrasound and infrasound. Ultrasound is used in medical imaging, where high-frequency waves are sent into the body and reflected back to create images. Infrasound, with frequencies below human hearing, can travel long distances and is used by animals like elephants to communicate. Natural events like earthquakes and volcanic eruptions can produce infrasound too. These forms of sound carry energy just like audible ones do. The difference is in the frequency, the scale, and how they interact with their environment. They can shake buildings, stimulate nerves, or map underground structures. They're invisible, but they're real. Another layer in the energy landscape. Sound energy isn't stored easily. Once produced, it either propagates or fades. That's why acoustic insulation works. It doesn't stop the production of sound, but it absorbs and diffuses the energy before it can reach other places. Foam, fabric, air gaps, they don't block the wave, they reduce its power. But stored sound can exist in a way. Recordings take the energy of sound and convert it into electrical signals, magnetic alignments, or digital data. When played back, that energy is released again, in a slightly different form. It's not the same air vibrating, but it's the same pattern of motion, captured, translated, and returned. Even language is shaped by sound energy. The rhythm of speech, the tone of voice, the cadence of a sentence, all of these rely on variations in energy delivery. A single word can be whispered, shouted, or sung, and each version feels different because the energy profile changes. Meaning, in practice, is layered on top of motion. So whether it's music, noise, speech, silence, or something in between, sound is always a form of energy in motion. You can't grab it. You can't store it in a box, but you can measure it, feel it, shape it, and be shaped by it. You don't need to see gravity to know it's there. You just have to let go of something. A pen, a rock, a grain of rice. If you let it slip from your hand, it falls. Not instantly, not with infinite speed, but predictably. Accelerating downward, pulled by something you can't touch. It doesn't feel dramatic. It feels normal. So normal that it's easy to forget it's happening at all. But gravity is one of the most reliable, far-reaching forces in the universe. It acts on all objects with mass, no matter how small, no matter how distant. It doesn't switch off. It doesn't alternate. It pulls, always. And it pulls with precision. You feel it most clearly as weight, not mass. That's how much matter something contains. But weight. The force that mass feels in a gravitational field. On Earth, that force keeps your feet on the ground, your drink in the glass, your organs in place inside your body. Without it, everything would float, drift, lose its bearings. Even your sense of balance depends on gravity. Your inner ear contains fluid that responds to orientation changes, using gravity as a reference. What's interesting is that gravity isn't just a constant pull, it's a source of energy. Not in the sense of creating energy, but in the sense of converting potential into motion. When an object is lifted, it gains gravitational potential energy, not because its mass has changed, but because it's been moved to a position where gravity has more room to work. Letting it go allows that potential to become kinetic energy, the energy of motion. That's the trade. Height becomes speed. You see this in a falling object. You see it in a roller coaster as it drops down a hill. You see it in a waterfall, in a landslide, in a swinging pendulum. Each one is a conversion, not a creation. The force is already there. The motion is the result of release. Even things that don't seem to move much are constantly adjusting to gravity's pull. Your muscles compensate for it every time you stand or sit. Structures are built to withstand it, with materials arranged to bear the load. Trees grow in ways that counterbalance it. Blood flows differently because of it. Your heart works harder to pump upward than downward. Gravity isn't loud, but it shapes every motion. On larger scales, gravity becomes even more central. It's what holds the moon in orbit around the Earth in orbit around the sun in motion within the Milky Way. These are not accidents, they're balanced systems, motion curving around force. An orbit is not about an object being pulled straight inward. It's about an object moving forward fast enough that its fall becomes a constant sideways glide. Like a stone spun on a string, but with no string. Just curved space and ongoing motion. That's why astronauts in orbit appear weightless. It's not because there's no gravity. Gravity is still pulling them and their spacecraft toward Earth. But they're also moving forward at the same rate they're falling. That balance creates continuous free fall. They're falling around the planet, not toward it. The sensation is one of floating, but it's really an ongoing fall with no impact. Gravity doesn't pull equally everywhere. It depends on mass and distance. More mass means a stronger gravitational pull. Less distance means that pull gets stronger fast. It follows an inverse square law. Double the distance, and the gravitational force becomes 1/4 as strong. That's why planets closer to the Sun move faster in their orbits than ones farther out. The closer they are, the stronger the pull, and the faster they must move to stay in balance. Massive objects like stars and planets shape space itself. That's the shift Einstein introduced. Not just a force pulling objects together, but a curvature of space-time that guides how objects move. Gravity is no longer just a tug, it's a map, and mass redraws the map. That curvature explains why light, which has no mass, can still be bent by gravity. As it passes near a massive object like a star or black hole, its path curves. Not because the light is being pulled in the traditional sense, but because the space it's moving through is curved. Gravity changes the shape of the road, not the behavior of the driver. That bending of light is called gravitational lensing, and it's been observed repeatedly, from stars seen behind the sun during an eclipse to entire galaxies distorted by the massive clusters in front of them. It's one of the cleanest demonstrations that gravity doesn't just affect matter, it affects everything that moves through space, even the space itself. Black holes are the most extreme case, regions where gravity becomes so intense that not even light can escape. Not because the black hole is infinitely massive, many are not, but because the mass is compressed into a small enough region that the escape velocity exceeds the speed of light. Anything crossing the event horizon, the boundary where escape becomes impossible, is effectively removed from the observable universe. But the gravity remains. It can still influence objects and light outside the horizon. The mass still curves space. But you don't need extremes to understand gravity's role. It's what holds rain to the ground, what makes a thrown ball arc downward, what gives a pendulum its swing. The energy in these systems flows because gravity makes potential energy real. Position becomes action. Elevation becomes motion. Tides on Earth are also a product of gravity, not just from the moon but from the sun as well. The moon's gravitational pull affects the oceans unevenly, causing water to bulge on the side facing the moon and the side facing away. As the Earth rotates, these bulges move, creating the cycle of high and low tides. The entire ocean is being stirred gently by distant motion. Even tectonic energy, the kind that causes earthquakes and volcanic activity, has a gravitational component. The heat driving those movements comes from radioactive decay and leftover energy from Earth's formation, but the movement of plates is resisted and shaped by gravity. Mountains rise until gravity pushes back. Rock shifts until pressure builds and breaks. The energy is stored and released in motion shaped by weight. When you walk up a hill, you're working against gravity. Your muscles do more than just move your limbs. They lift your entire body upward against a constant pull. That effort isn't wasted, it becomes stored energy. Stop at the top and you've banked potential. Run back down and it becomes speed. Gravity's involvement isn't visible, but it's steady. Even in sleep, gravity doesn't pause. It affects circulation, posture, the pressure on joints. Long-term space travel, where gravity is much weaker or effectively absent, shows how deeply the body depends on it. Muscles shrink. Bones lose density. Blood redistributes. The body adapts but slowly, and not always in helpful ways. Gravity isn't just something we tolerate, it's something we're built around. And while we often think of it as heavy or confining, gravity is also graceful. It allows balance. It enables flow. Rivers run downhill not because they prefer lower ground, but because gravity draws them there, carving valleys over centuries. Leaves fall, snow accumulates, glaciers move. Not in sudden drops, but in slow, constant responses to weight and slope. Every movement that returns to ground, every structure that holds its shape, every orbit that remains stable, all are examples of gravity's influence. It doesn't push or twist or spark. It simply pulls, always inward, always steady. And in that pull, motion finds its path. From a distance, the world seems stable. Objects hold their shape. Surfaces appear solid. Motion seems optional, something things do when pushed or pulled. But zoom in far enough, and that sense of stillness disappears. What looks motionless from the outside turns out to be constant motion underneath. At the smallest scales, below atoms, below electrons, energy never settles. Even in perfect isolation, even at absolute zero, there's motion. It never goes away. This is the quantum scale, a regime where the rules of classical physics no longer apply cleanly, and where energy doesn't behave the way we're used to. Particles blur into waves. Positions turn probabilistic. Interactions unfold not in smooth curves, but in discrete sudden steps. And through it all, motion persists. Take an atom. It seems like a fixed structure, a nucleus in the centre, electrons in orbit. But electrons aren't little balls circling like planets. They don't have precise orbits or fixed positions. Instead, they exist as probability clouds, regions where the electron is likely to be found but never guaranteed. Those clouds represent energy levels shaped by quantum rules. An electron doesn't slowly spiral from one level to another. It jumps, a discrete transition. That jump isn't a metaphor. It's a real change in energy state, and it either happens or it doesn't. No in-between. This discreteness is one of the defining traits of quantum systems. Energy is not continuous. It comes in packets, quanta. Photons are packets of electromagnetic energy. Phonons are packets of vibrational energy in a solid. Even energy stored in atoms follows this rule. Electrons can only occupy certain levels, not anywhere in between. That's why atoms emit light at specific frequencies when excited. The electron drops from one energy state to another, and the difference comes out as a photon with a precise wavelength. Not a glow, a step. But even when nothing seems to be happening, something is. Quantum systems have what's called zero-point energy, the lowest possible energy state they can occupy. Not zero energy, 0 point. Even at absolute zero, where thermal motion ceases, this baseline jitter remains. It's built into the rules. Particles can't be perfectly still, because perfect stillness would require them to have both exact position and exact momentum, which quantum mechanics forbids. That uncertainty is not a bug, it's a principle. The Heisenberg uncertainty principle states that certain pairs of properties, like position and momentum, cannot both be precisely known at the same time. The more precisely you know one, the less precisely you can know the other. It's not a limitation of tools or measurement, it's a feature of nature. The result is a constant, unavoidable fuzziness, a jitter in the fabric of matter itself. You see it in vacuum fluctuations, random brief appearances of particle-antiparticle pairs in empty space. These virtual particles don't last long, they pop into existence, interact briefly, and annihilate each other. But their presence is detectable. Their energy leaves fingerprints, like in the Casimir effect. A tiny force that appears between two metal plates in a vacuum, caused by the suppression of vacuum fluctuations between them. Nothing is touching them, but something is happening. Empty space isn't empty. That background motion, the jitter of fields, is what the quantum world is built on. Every particle is a ripple in a field. Electrons, quarks, photons, all are excitations like waves on an invisible surface. The particle you detect is the crest of that wave, but the field is always present, even when the particle is not, and that field is never fully still. In quantum field theory, particles don't interact like billiard balls. They interact by exchanging other particles, carriers of force. Photons carry the electromagnetic force. Gluons carry the strong force. Bu and Z bosons carry the weak force. These exchanges are not continuous flows but sudden transfers. Tiny bits of energy passed back and forth, shifting the state of each participant. Even gravity in quantum terms would have a particle, the graviton, although it hasn't been detected. At this scale, energy is not easily separated from probability. You can calculate the likelihood of a particle being in a certain place or state, but you can't predict the outcome of a single event with certainty. Quantum mechanics only offers probabilities. The exact result is unknowable until it's measured, and even the act of measurement changes the system. This might seem abstract, but it has very real consequences. Quantum tunneling is one example. A particle appears on the other side of a barrier it doesn't have enough energy to climb. Classically, it shouldn't happen. But quantum rules allow a small probability of the particle's wave function extending past the barrier, and sometimes that's enough. The result isn't a cheat, it's a statistical event. Enough tries, and it works. This is how nuclear fusion happens in the Sun. The core isn't hot enough by classical standards for protons to overcome their mutual repulsion, but quantum tunneling allows them to get close enough for the strong force to take over and bind them. Without quantum effects, the Sun wouldn't shine. Its light is built on chance, repeated billions of times a second, enough that the result feels continuous. Superconductivity is another quantum effect, a state where electrical resistance drops to zero in certain materials at low temperatures. Electrons, instead of scattering off atoms, move in coordinated pairs called Cooper pairs. Those pairs behave like a quantum wave, able to travel through the material without losing energy. No friction, no heat loss, just sustained motion. A quantum current that once started can loop indefinitely. Quantum systems also underlie lasers, transistors, LEDs, and much of modern computing. These aren't metaphors or surface-level designs. They depend on the precise manipulation of energy levels, wave functions, and tunneling effects. Quantum mechanics isn't just a description of the invisible, it's the architecture of everyday technology. Even biological systems show quantum behavior. In photosynthesis, energy captured from light is transferred through a network of molecules with remarkable efficiency, likely due to quantum coherence, where the energy explores multiple paths simultaneously before settling on the most efficient one. The process doesn't pause to calculate. It happens because quantum rules allow it. Quantum energy is jittery, discrete, unpredictable, but never absent. Even when it looks like nothing's happening, there's a baseline hum. a field vibrating just slightly, a particle blinking in and out of possibility. The classical view, objects at rest in silence, is an approximation. Underneath, everything vibrates, not symbolically, but physically. Even in the coldest vacuum, energy remains. The energy in the universe doesn't stay in one place. It moves, transforms, spreads, contracts. It doesn't sit quietly in pockets. It flows through fields, across stars, into matter, out of radiation. From the smallest jitter of a quantum particle to the structure of entire galaxy clusters, the pattern is the same. Motion driven by energy, and energy shaped by the rules of physics. On cosmic scales, gravity becomes the architect. It draws together gas, dust, and dark matter, shaping the formation of galaxies and stars. But the energy present isn't only gravitational, it's thermal, kinetic, nuclear, electromagnetic, all the familiar forms, scaled to astronomical proportions. A single galaxy can contain hundreds of billions of stars, each one producing energy through fusion. Around those stars are planets, many with active cores, atmospheres, magnetic fields. Between the stars lies interstellar gas, carrying thermal energy. Surrounding the galaxy, a halo of dark matter holds everything in place, not by direct contact, but by the gravitational field it creates. It doesn't emit or absorb light, but it shapes the motion of stars and gas. Its presence is known by its effects, not its visibility. Multiply that one galaxy by hundreds of billions, and you start to approach the known universe, not as a static field, but as a moving, changing structure. Galaxies rotate, drift apart, collide. When they merge, their stars rarely collide directly. The distances are too vast, but their gas clouds crash, compress, trigger new waves of star formation. Energy redistributes. New light appears. The change is smooth, but follows the same rules. And in between galaxies, space itself expands. That expansion isn't just a backdrop, it's a dynamic feature. One that stretches the wavelength of light travelling through it, shifting it toward the red end of the spectrum. This redshift is one of the main pieces of evidence that the universe is growing, not because galaxies are moving through space, but because space itself is stretching, carrying the galaxies with it. That expansion carries energy implications. As light travels across expanding space, its wavelength grows, and with it, its energy decreases. It doesn't vanish, it's redistributed. What was once high-energy radiation becomes microwave background. The universe cools over time, but not passively. The cooling is the result of expansion, of space changing shape. The cosmic microwave background is one of the most direct glimpses into that early energy. It's a faint, uniform glow of radiation that fills the universe, left over from a time when matter and light first separated. Before that moment, the universe was too hot and dense for atoms to form. Photons scattered constantly. But once things cooled enough, electrons and protons combined into neutral atoms, and light could travel freely. That light is still travelling, stretched and cooled but intact. Today, that background radiation measures just a few degrees above absolute zero. It's uniform to 1 part in 100,000, but those tiny fluctuations in temperature reveal the seeds of structure. Slight variations in energy density eventually became galaxies, clusters, stars. The universe didn't start uniform, and it didn't stay that way. Energy differences amplified, guided by gravity, sculpting the visible cosmos. But the total energy content of the universe isn't just matter and light. In fact, ordinary matter, everything made of atoms, only accounts for about 5%. Another 27% is dark matter. And the remaining 68% is something stranger. Dark energy. Dark energy isn't a substance. It doesn't clump or emit. It's a property of space itself. a kind of pressure that accelerates the expansion of the universe. It was first inferred from observations of distant supernovae, which appeared dimmer than expected. The conclusion: they were farther away than predicted. The expansion was speeding up. That acceleration takes energy. Not energy we can isolate or tap into, but energy that reshapes large-scale geometry. The equations of general relativity allow for it. A cosmological constant, or something similar. But its exact nature remains unknown. What's clear is that it dominates the large-scale behaviour of the universe. Whatever it is, it exerts pressure with negative gravity, not pulling matter together, but pushing space apart. On top of that, the universe isn't infinite in age. The expansion started from a hot, dense state, what's now called the Big Bang. Not an explosion into space, but the rapid expansion of space itself from a point of extreme density. That beginning marked the release of enormous amounts of energy, cooling and thinning as space grew. From that energy came particles, from particles, atoms, from atoms, stars. The early universe was almost entirely hydrogen and helium, the lightest elements. Heavier elements were forged later, in stars and supernovae. Fusion reactions in stellar cores built up the periodic table, slowly converting the initial raw material into a richer mix. Exploding stars scattered those elements into space, where they could collect, cool, and eventually form planets, life, technology. Everything you see now is built from that transformation. The iron in blood, the carbon in skin, the oxygen you breathe. All of it came from the interior of stars, powered by fusion, guided by gravity, released by collapse. The energy was always moving, from core to surface, from star to dust, from dust to structure. And that movement continues. Black holes grow, galaxies spin, clusters drift, cosmic filaments stretch across the void, connecting islands of matter. Simulations show that the universe forms a kind of web, dense nodes where galaxies form, and thin threads of gas connecting them. In between, vast empty spaces, not truly empty, but sparse, quiet, stretched. Some of this energy is visible, most is not, but none of it is still. Particles collide, radiation pulses, magnetic fields twist. Even neutrinos, nearly massless particles, stream through space in massive numbers. Every second, trillions of them pass through your body, unnoticed, unabsorbed. They carry energy, but barely interact. Still, they are part of the overall budget. Gravity ties it all together, but energy is what makes it active. The shape of the cosmos, its expansion, its structure, its age, all depend on how energy is distributed. The faster it expands, the colder it becomes. The more dense it gets, the more structure it forms. The balance is delicate. Too much energy early on, and nothing would have settled. Too little, and everything would have collapsed. What exists now is a consequence of that narrow range, and the energy continues, not in steady pulses or clean lines, but in flux, spread across light, matter, motion, pressure. There's no single reservoir, just a system that evolves step by step, particle by particle, galaxy by galaxy. When you use a battery, it runs out. When a candle burns, it finishes. When a phone dies, the screen goes dark, so it's natural to wonder, is energy something we're using up? If it powers everything, can it run out? The answer depends on what you mean by use. Energy doesn't disappear. That's one of the most firmly established ideas in physics, the conservation of energy. It can be transferred, transformed, spread out, concentrated, degraded, but not destroyed. The total amount of energy in a closed system remains constant, always. So when a battery dies, the energy isn't gone, it's just moved. The chemical potential inside it has been converted to electrical energy, then to heat, light, or motion, depending on what the battery powered. The energy has changed form and likely spread out into the air, the surrounding material, the environment. What you've lost isn't the energy itself, but its usefulness. That's where the idea of availability comes in. Not all energy is equally usable. High-quality energy, like electricity or concentrated heat, can do more work. It can drive engines, run electronics, charge other systems. Low-quality energy, like ambient warmth or diffuse radiation, is harder to harness. It's still energy, but not in a form that's easy to direct or convert. This difference is captured by the concept of entropy. As systems evolve, entropy tends to increase. That doesn't mean disorder in the everyday sense. It means the energy becomes more evenly distributed, more randomized, harder to extract work from. A hot object in a cold room cools down. The heat spreads, balancing the temperature. The energy is still in the room, but no longer concentrated. No longer useful for pushing a piston or running a circuit. In that sense, yes, we use up usable energy. Not by making it vanish, but by transforming it into forms that are harder to recover. Engines burn fuel, converting chemical potential into kinetic energy and heat. Lights convert electricity into photons and warmth. Muscles use stored food energy to contract. Every step reduces the ability to recover that energy in a concentrated form. The total energy stays the same, but the structure changes. You can think of it like spending money into 1,000,000 accounts you can't withdraw from. The wealth still exists, just in a scattered, inaccessible form. Technically present, but practically gone. This is why energy systems need constant input. The sun powers life on Earth not because energy is being created from nothing, but because we receive a constant stream of concentrated energy in the form of sunlight that hasn't yet degraded. That input drives growth, weather, motion. Without it, the planet would drift toward thermal equilibrium, a steady, uniform temperature with no gradients left to exploit. Every device you use, every machine, every cell in your body, all of them rely on taking in structured energy and releasing less structured energy in return. The process is continuous. You never use energy once. You use its difference, its capacity to cause change, and then return it in a more even, less directed form. The same logic applies on larger scales. A star converts nuclear potential into light and heat. That energy spreads through space, eventually absorbed by matter, heating dust, feeding plants, warming planets. But once it radiates out and disperses, it doesn't gather itself again. The universe doesn't recycle energy in perfect loops. The gradients that allow work are gradually smoothed out. Some processes are more efficient than others. A hydroelectric dam can convert falling water into electricity with relatively little waste. A car engine, by contrast, loses a large fraction of its input energy as heat. But even the most efficient systems still produce waste heat. Entropy always increases. That's not a flaw, it's a rule. You can reduce energy loss locally, insulate a house, streamline a machine, improve battery design, but you can't stop the overall drift toward less usable forms. That drift is what powers time's direction. It's what makes history irreversible. A spilled cup of coffee doesn't leap back into the mug. The heat doesn't flow from the cooler air into the warmer liquid. The atoms don't unscatter. That irreversibility defines the arrow of time, not because energy is being lost, but because its arrangement becomes less specific. It spreads, and once it spreads, recovering it into its original ordered form takes external input. You can recharge a battery, but only by spending energy elsewhere. You can freeze water, but only by applying work. Restoration isn't free. It costs more energy, and the net result still involves entropy increasing somewhere. This is the deeper meaning behind energy use. You're not draining the universe, you're reshaping it. Every action transforms the state of a system, not by deleting energy, but by pushing it from organized to disorganized. That reshaping has limits. Some energy is recoverable, some is not. The universe as a whole still contains the same total energy it always has. But as stars burn out, as heat spreads, as gradients even out, the options for useful work diminish. In theory, if left alone, the universe would trend toward a state of maximum entropy, a kind of equilibrium, where all matter and energy are evenly distributed. No stars, no engines, no systems, just uniformity. That's called heat death. But we're not there, not close. Stars are still forming, galaxies still rotate, matter still clusters under gravity. On human timescales, there is still plenty of usable energy, more than we can tap, more than we fully understand. The universe is active, it's not winding down yet. What matters more than quantity is access. Can the energy be concentrated? Can it be directed? Can it be stored, released, cycled through systems that build or move or evolve? That's what determines usefulness. And that's what all life, technology and natural processes depend on. So when something runs out of energy, a flashlight dims, a satellite falls silent, a person gets tired, it hasn't broken the rules. The energy has just finished its work and taken a less useful shape. Not gone, just spread. You're not separate from the energy flow. You're inside it, shaped by it, moving with it. The energy that powers your body doesn't come from nowhere. It arrives through food, air, light, warmth. It enters your system, passes through chemical pathways, becomes motion, thought, sensation. And then it moves on. Everything you do requires energy. Blinking, breathing, standing still. Even when you sleep, your body's busy, maintaining cells, regulating temperature, repairing tissue, processing memory. It doesn't shut off, there's no pause button. What looks like stillness is still activity, just redirected inward. The energy comes in mostly through food. You eat carbohydrates, fats, proteins. Those molecules are broken down in your digestive system, then absorbed into the bloodstream. Glucose, amino acids, fatty acids. These are the input materials. But they're not the energy yet. They're just chemical structures holding potential. Inside your cells, that potential is accessed. In a compartment called the mitochondrion, often described as the powerhouse of the cell, chemical bonds are broken in a controlled series of steps. That process is called cellular respiration. It extracts energy by gradually releasing it, transferring it to a molecule called ATP, adenosine triphosphate. ATP is the immediate energy currency for almost every cellular process. When a cell needs to do something, contract a muscle, transmit a signal, divide, it uses ATP to power the step. The body doesn't store much ATP at once. It's made on demand, used quickly, remade constantly. At rest, your body produces and uses around your own body weight in ATP each day. During intense activity, that number increases. It's not because you're storing more, it's because the turnover rate goes up. The energy is always flowing, from intake to output, through countless small steps. Even thinking takes energy. The brain, while only about 2% of your body weight, uses around 20% of your resting energy. Neurons fire, synapses reset, ions move across membranes. Each signal you process, each memory you retrieve, involves molecular motion. It doesn't feel like effort, but the energy use is constant. The warmth of your body is also energy. Maintaining internal temperature is not passive. You're constantly generating heat, and your body works to keep it within a narrow range. That's why you shiver when cold, small rapid muscle contractions that generate heat, and why you sweat when hot, evaporation cools the surface. Both are active processes, both use energy. Movement is more obvious. Muscles contract when actin and myosin proteins slide past each other. That sliding requires calcium release, ATP breakdown, ion transport. What feels like a simple stretch or step is the result of countless small events, each powered by chemical energy, and once the motion is complete, more energy is used to reset, to pump calcium back to re-establish gradients to prepare for the next movement. Even stillness isn't passive. When you sit quietly, your body is balancing blood pressure, digesting food, maintaining posture, keeping your organs in sync. Each beat of your heart takes energy. So does each breath. So does filtering waste in the kidneys, producing hormones, repairing tissue. These aren't optional background tasks. They're continuous energy conversions happening all the time. On a larger scale, you're not isolated. The energy you consume came from elsewhere. The food you eat is made from plants or animals. Plants get their energy from the sun through photosynthesis. They capture photons, convert carbon dioxide and water into sugars. Animals eat those plants, or other animals that ate those plants. That energy path can be traced. Photon to plant to molecule to motion. At every step, energy is transferred, changed, passed along. You return energy too. The heat your body emits warms your surroundings. The carbon dioxide you exhale becomes part of the air. Waste becomes food for bacteria and insects. Even in rest, you're contributing. The flow doesn't stop at your skin. It continues outward, through radiation, contact, movement. If you exercise, you increase the throughput. More energy is demanded, more is used, more is released. But the principle doesn't change. You're not making energy. You're converting it from stored molecules into kinetic energy, heat, momentum. Afterward, you recover. The body rebuilds, restores balance, replenishes its supply. That recovery also takes energy. The entire life cycle is an energy process. Growth, maintenance, reproduction, aging. Each stage involves different energy demands, but the same basic mechanism: intake, transformation, output. Cells specialize, tissues coordinate, systems adjust. The complexity doesn't change the rule. Nothing happens without energy moving through. Even memory, emotion, attention. These are not separate from the physical. They are patterns of activity in the brain, which itself is a physical structure powered by chemical gradients. When you learn something, connections change. When you feel something, neurotransmitters shift. These aren't symbolic changes. They're real, measurable energy events. That includes fatigue. When you're tired, it's not just a mood, it's a signal. Your energy systems need rest, not because energy has run out completely, but because the processes that support high activity need time to restore balance. Waste products must be cleared. Ion gradients must reset. Resources must be reallocated. Even sleep is part of the cycle, not a break from it. You're never fully disconnected from the larger flow. The air you breathe carries oxygen to support respiration. The water you drink supports circulation, digestion, temperature control. The light on your skin affects hormone levels, circadian rhythms, even cell behavior. You're not a closed system. You're part of a network. Constant inputs, constant outputs, constant adjustment. Even your physical mass, your cells, bones, fluids, are built from material that was once outside you. The atoms that make you up were once part of soil, air, water, food. The energy those atoms carry is the same as what moves through the rest of the universe. The difference is arrangement, not origin. And eventually, the energy and matter that make up your body return to the system. Decomposition is not disappearance, it's transformation. The energy stored in your tissues becomes warmth, motion, fuel for microorganisms. The carbon re-enters the cycle, the elements disperse, nothing vanishes, nothing is removed, the flow continues. If you follow energy long enough, it always leads somewhere else. Nothing finishes in one place. It moves, it transforms, it takes on new forms, then continues. Systems end, but the energy doesn't. It leaves one boundary and enters another. That's true for everything that runs: engines, organisms, planets, stars. Each has a life cycle, a beginning and an end. But that cycle isn't isolated. It connects to others. A car burns fuel and moves forward, releasing heat and gases into the air. A star burns hydrogen, shines for billions of years, and eventually collapses or explodes, spreading heavier elements into space. The energy that powered it doesn't vanish. It just changes form, becomes part of something else. The same goes for all systems, large or small. A tree grows by absorbing sunlight, water, carbon dioxide. When it dies, its matter and energy return to the soil and air. The molecules don't disappear. They dissolve, decay, spread. The sunlight it stored in its wood is released as heat when it breaks down or burns. The cycle completes, but the flow doesn't stop. Even the structures we build, houses, machines, tools, follow this pattern. They don't hold energy perfectly. Over time, materials wear down, systems lose efficiency, heat escapes. Eventually, everything built returns to simpler pieces, scattered or reused. But the energy it once contained isn't gone. It's just dispersed. On the larger scale, the universe itself is doing the same. Galaxies drift apart. Stars burn through their fuel. Energy spreads. The usable differences, the gradients, become fewer. But the energy remains. Light from stars continues across space. Heat from particles continues radiating outward. The background temperature drops, but never hits zero. There's always some motion, some vibration, even at the edge of emptiness. The systems that once shaped energy will fade, but the energy that passed through them still exists. You can trace its path. You can measure its residue. You can watch its effects ripple outward. From one scale to the next, the rules don't break. They stretch, adjust, apply again in a new shape. That's why energy doesn't require direction. It simply follows the rules. From high to low, from concentrated to dispersed, from one form into another. You are one of those forms. You weren't separate from it before, and you won't be after. The flow doesn't start with you, and it won't end with you. But you carry it in every step, in every breath, in every thought. Nothing stops. There are pauses, transitions, redistributions, but no ends. Only changes in shape, changes in structure, changes in what the energy becomes next.